Good morning, everyone. We are Team Astronomy, or as we named ourselves, Team Exomites. Let us now introduce ourselves. We are a group of 12 high school students keen on learning about the mysteries of the universe. We were helped by our two incredible mentors, Anjali ma'am and Swastik sir. With their guidance, we challenged ourselves to find exoplanets that would lie in the habitable zone. Now, we will be taking you forward our progression in the project, starting with a few initial topics we were introduced to.
So the first topic that we want to introduce you to is the radial velocity method of detection of planets. This method is also called the wobble method because it attempts to detect the wobble of a star which has an exoplanet surrounding it. Why this happens because when a planet goes around when a planet goes around a star, it causes the star to move away from its center due to the gravitational pull, and the star appears to wobble, as you can see in the GIF over here. It is not actually wobbling; it is just going around its barycenter, which is the center of mass of the entire system. We can detect this using the Doppler shift of light, which is basically the change in the wavelength of the light as the source of the light moves away or towards us. When the source of the light moves away from us, the wavelength of the light expands and it causes to appear redder. And when the source of the light comes towards us, the wavelength of the light contracts and appears bluish to us. We call this the red shift and blue shift. If we observe a periodic redshift and blue shift in the light coming from the star, we can infer that there is a wobble happening, that the star is wobbling a little bit. And if there is a wobble, we can tell that there is a planet orbiting the star, because generally the planet would cause the wobble. However, there are a few limitations to this method. The first is that at times, like, we can't tell whether the wobble is caused by one object around the star or multiple objects, because the amount of wobble caused by one planet could be similar to the amount of wobble caused by two or more planets due to their masses and gravitational effects. The other limitations that we can think of was that at times the wobble of the star is so little that it is very difficult for us to detect, because it's not visible with the naked eye, and we need very, very precise instruments that at times cannot record such a minute wobble. So this is not the primary method that we use to detect exoplanets.
Hello everyone, I'll be talking about the second method that we studied, that is called the transit. The transit method consists of regularly measuring the luminosity of a star in order to detect the periodic decrease in luminosity associated with the transit of an exoplanet. So this method is mainly based on vision that aims to indirectly detect the presence of one or more exoplanets. It is when a planet orbiting around its star comes in front of it from our point of view. Since the planet is overshadowed by the star, it appears black. We can see it in the GIF over here. This is a simulation of the Venus transit. We see that the Venus planet is black in color because of the overshadow. It is a very famous method, and almost 90% of the exoplanets were discovered through this method. It is also more of a luck method because of its many limitations. Some of these limitations are conditions. Suppose we need the alignment of the planet and the star, and also the orbital position of the star. The planet. If the planet is revolving above the star, then we would not be able to see the transit of the planet. Yes.
Nuclear fission and fusion. Nuclear fission is a process in which an unstable nucleus splits into two nuclides and emit neutrons. There are two types of nuclear fission: spontaneous fission and induced fission. Nuclear fusion is opposite of nuclear fission. It is a process where two lighter nuclides combining together, releasing vast amount of energy. Fusion reaction occurs in a star where two hydrogen nuclei fuse together under a high temperature and pressure to form nucleus of helium atom.
Apparent and absolute magnitude. So what exactly is it? So many years ago, when the astronomers looked up at the sky, they gave a magnitude to the brightest star in the sky as 1, and the stars painted in that as 2, 3, 4, and so on till 6. But when the telescope was discovered, they saw even more stars which were not even visible to the naked eye, and they gave them 7 and above. So this is apparent magnitude. In very, very simple terms, it is the brightness of the star when viewed from Earth. And what is absolute magnitude? If we keep that same star away at a distance of 10 parsecs, 1 parsec is 3.2 light years. Then we look at the star. That is the brightness of the star, and that is absolute magnitude. Then why 10 parsecs? Suppose if we stand near a bonfire, if we are too close to it, then it's burning hot, and if we are too far away from it, then we don't feel the warmth of the bonfire. So 10 parsec is a distance like that. It is not too far away or not too close. And did you know Cohort is a star in which the apparent magnitude is lower than the absolute magnitude? Keep in mind that the brightness of the star, when it's lower, it is the brighter. Thank you.
So, we were talking about exoplanets and we named ourselves as exominds. So, what basically is exoplanet? Exoplanet is basically the planet which is not in our solar system and belongs to a foreign star. Now, let's talk about the most interesting part of our problem. That is our whole GSS program. That is our problem statement. So, what is exactly our problem statement? Using the data from the NASA's exoplanet archive, we have to find out the habitable zone of the star, the foreign star, and find whether the corresponding planet of the star is in the habitable zone or not. And then we need to plot the graph of the effective stellar temperature versus the average habitable zone. So let's see what happens next.
Before we dive right into how we solved a problem statement, here's the step-by-step process which will give you a brief picture. So first step was collecting the data. The second step was finding the relations for the calculations. Then we had to generate and plot the then we had to develop and execute the codes for the calculation. Next, we had to generate and plot the graph. And the last step was analyzing the graph and coming to a conclusion, hence solving a problem statement.
The data from the NASA exoplanet archives after importing to the Excel was imported in Python, where data cleaning was performed. The formulas were now going to be coded in Python. We went through many formulas, but we used the one which gave us the most suitable results. For luminosity, we used the equation of luminosity of a black body. A black body is a physical body that absorbs or emits all frequencies of electromagnetic radiation. Here, luminosity is found when sigma is multiplied by the temperature to the power 4, whose result is multiplied by the result of 4 into pi multiplied by the square of the radius of the star. In this equation, sigma is the Stephen-Boltzmann's constant. So now we have the luminosity, and from luminosity, we are able to find the habitable zone. So for in a habitable zone, we calculated it by multiplying the root of the luminosity found by 0.8, which was then added to the radius of the star, giving us an inner habitable zone. For the outer habitable zone, we did the same, except the root of luminosity was multiplied by 1.2. And then the result of what was added to the radius of star, giving us the outer habitable zone.
Now, let's talk about coding the formula for the calculations. And this was again the most important part of our whole presentation because without coding we cannot find the results. So, what did we use and why did we use it? So, we use Python as a primary language because again it is really good for data analysis. And we use few libraries. Those were pandas, NumPy, Matplotlib, and Seaborn. And how did we use them? So, I'll tell you now. First of all, we started off and then we used pandas in order to import the data and do the data cleaning. And what did we import? Specifically, we included planet mass, stellar radius, stellar temperature, and many other columns. And after that, we created a function for luminosity, inner habitable zone, and outer habitable zone. And then we found the average of it. After that, for plotting the graph, we use Matplotlib and NumPy for the calculations. And for plotting the graph and fitting the best curve, we use seaborne. We'll show you the graph in the next slide. So this was our graph. And again, this is the most important part of our whole presentation. Now, we use Python for the accuracy, and we can observe many good things here. The very important thing that we observe here is that the log of effective stellar temperature and the log of habitable zone is plotted here. So we can see that when the average habitable zone is moving away from the star, the effective temperature is rising up. Why does this happen? And why did we use this thing? Again, how did we define habitable zone is how the graph is. So we define habitable zone in a way that the liquid water can sustain there, and the range of temperature in which the liquid water sustain in specific pressure and temperature is 0 degree to 100 degree centigrade. And this is why when the temperature is increasing, the liquid water might not sustain, and the liquid water might not sustain, and it might get vaporized. And when the temperature is decreasing, the liquid water might get solidified. So this is why the temperature is very important factor. Now, let's talk about the conclusion. What is the conclusion and how did we find it? So, conclusion. None of the exoplanets lie in the habitable zone. This is because of few errors that we had. Our data was not good enough. Second, so we have to do the data cleaning, and in that, many exoplanets were shut off. And that is why we could not find any exoplanet in our data. As our data were reduced to around 4,000 to 614. After that, the effective temperature increases, the distance of the habitable zone from the star is also increases. And hence, what we find, effective temperature is directly proportional to the distance.
That's right. So we team Exominds, we wanted to aware people about space and about our project. So we also made a website. It is not yet published, but it will soon, and you can check it out.
We also made social media accounts to share our research among the world so that everyone can follow along our progression.
Guest speaker. Team Examines was very fortunate to get to interact with Sir Jayant Murthy, who's a renowned astronomer and physicist around the globe. We would like to thank him for guiding us as learning from the best in this field helped us to go about our problem statement when we were overwhelmed by the complexity of it.
Finally, we would like to thank some very important people who have been crucial to this journey. We want to thank SSERD itself for this great opportunity in the form of JSS. We also want to thank our supervisors, Ma'am Anjali and Sir Swastik, who have been extremely helpful to us in solving our doubts and explaining every detail. And lastly, we are grateful to all our cohort members for making this an enjoyable and amazing experience.
So now we are at the end of our presentation. So before going, we'd like to end it with a quote. That is, we are an impossibility in an impossible universe. And that is why we are looking for another impossibility in another exoplanet. Thank you so much. And now we are open to questions.
Thank you so much, team. So we have the link for the questions posted up in the chat. So any questions that the audience have are to be posted there. Before that, I would like to make special mention to Sridhar sir here with us today, and also Margarita ma'am. Sudhir sir happens to be the director of CBPO ISRO, and we have Margarita ma'am from Indian Institute of Astrophysics. I welcome you both to this session, ma'am. We are honored to have you with us today. So, without further ado, I would go ahead with the questions. Okay, we have the first questions for the team astronomy coming here. Team?
Yes, I like to answer that. The number of planets that are discovered using the transit method are 3,343.
Okay. We have another question.
Okay, I would like to answer this question. So, the significance of habitable zone. This is a very good question because, again, as we know what is a habitable zone, and we should know how we define it first of all. So, how Team Exominds define habitable zone for this project is that the liquid water is sustained there. And when liquid water can sustain there, there is a possibility of life because the most important factor for living is water. And that is why there is a lots of significance for the habitable zone. Yes. So, yes, this question is again important. Is there any outliner in your graph? Yes, we had two graphs basically. The first graph had an outlier. Why? Because we used the formula which we used was an approximation. In that case, what happened was there was a big giant, and there the habitable zone, the temperature was really high, around 27,000 degree Kelvin, and the habitable zone lied near the star, and that was the outlier for our graph.
Team, anyone would like to address this?
Yes. Okay. You may need to look at. So we
Yes.
would surely look after this thing. Again, we were looking for the liquid water in the first case. Now, our second step would be to look for the gravity and many atmospheric things. So we'll surely look after this, sir. Thank you so much for your suggestion.
Okay, thank you so much, team. So now we go ahead with the next team. So we have.
We have another question in the chat.
Okay.
Yep.
So we have another question posted in the chat by Dr. Shashidhar sir. So habitable zone is for humans, I suppose. How about possibility of evolution of life independently, non-humans? So would the team like to take up that question?
Yes, we would love to take that question. And how about the possibility of evolution of life independently? So, yes, here the question is really good. And again, the habitable zone is for human. Yes, no. There is habitable zone is basically how we define it again for the liquid water sustainability. So, liquid water is important for all other beings present in the whole evolution. So, liquid water is where the life starts. Again, before when the earth was really, really hot, then the ozone layer formed, and then the liquid water. The liquid water was the backbone for the life. So that is why independently there is a possibility of evolution. So yes, there are many other possibilities as well that without liquid water there can be life such as bacteria which are present in the space in the vacuum. So yes, there are many other possibilities too, sir. Yes, sir. Few organisms can take the water from the air moisture, but again, how we define it, the liquid water in the habitable zone is important for us. As a humans, we are looking for more other species, and that is why liquid water is the most sustainable thing we looked after.
Team, you have another question. I'll be sharing it. Okay. This is from Margarita Ma'am.
So the biggest drawback of radial velocity is that like there are many limitations. Like I mentioned, there is the limitation of not being able to tell how many planets are there. It's difficult for us to tell what the mass of the planet is because of the gravitational effect as well, and also that we can't, at times we can't detect the wobble. However, the biggest limitation of transit would be that it depends a lot on chance and on a lot on aligning of all, like the planet, the exoplanet Earth, and the star that the exoplanet is from. We need there to be a near perfect eclipse for us to be able to detect the light source. So that, like, while it's not a very like while even though we have hypothesized that there could be at least one planet per star, the transit method won't be able to help us in detecting all of the planets, because the aligning of the planets from between Earth and the star could be different. So these are the two main drawbacks of both the detection methods that we mentioned.
The same goes for the radial velocity method. Imagine if the all the orbits are flat to us, we cannot determine the wobble also, because wobble you can determine only if the star is going back or forth. Yeah, but if it is in the flat projection to us, we cannot determine it either. So this is the biggest drawback of this.
Yes.
So why I ask you this is that you know how many planets were detected by both methods, approximately 4,600, and there are some 5,000 candidates and so on. Just imagine if so many planets detected by just this chance alignment, how many planets would be there by projection in our galaxy?
Probably billions, the same amount as the stars at least.
Exactly.
Maybe more per star. So
Exactly. Thank you.
Thank you so much, ma'am. It would be great if you could suggest the team as to how to proceed further with the project. So it would be really great if we can give some guidelines as to how to proceed with the project and what to look in for.
Okay, thank you. I will talk to Nikita and Sujay. Great.
Thank you so much, ma'am. And we have Sudhir sir as well. Sudhir sir, even if you have any comments to make on the team, suggestions to be given, please do so, sir.
It's amazing because I never expected that these kids would go to that extent, because I can only compliment the thing and all the best to the kids. I never expected probably Python and all these things, no, maybe at BTech level or beyond. When these kids get exposed to such kind of environment, both knowledge wise and information wise, I can only compliment. I don't have any words to say so. But all the best, kids. You keep doing this kind of research, maybe beyond. That's all I want to say. Thank you.
Thank you so much, sir. Shashidhar sir, do we have any comments, inputs from you for the team?
Oh, excellent. I'm wonderstruck. The level of thinking, thought process, presentation skills, amazing. I suggest you also broaden your thinking out of the sphere of humans. Go for life as a holistic approach. Thank you.
Thank you so much, sir. So I guess there was another question posted by you, right, in the chat, if I'm not wrong. What if the planet does not rotate on its own axis like the Earth? What if only one face of the planet is facing the star? The other side can be habitable. So team, would you like to answer that question?
I'll answer it. So the thing is that the other side, there will be no warmth. It will be a very, very dark and cold place. So life won't be sustainable there, and it won't be habitable without the warmth of the star.
Thank you so much.
In our definition of habitable zone, there might not be the life. But again, if we define it on some other way, if there is atmosphere present, then the warmth might, the warmth might spread around, and there are many other factors that can, affect that area. So in our definition, we say that it's really really hard. But again, if we define it in the other broader perspective, yes, there can be lives also.
Okay, we also have another question from Margarita Mom. I just noticed it now. Imagine Mercury, can life be possible on its other side? I guess it follows the same. Team?
So, ma'am, we're not really sure exactly if it lies in the habitable zone or not, but I'm assuming because it's too close that it might, like by our definition at least, it might not be able to sustain life. However, there are many factors that can affect life, and we don't exactly know where, like, we don't know completely everything about life. So, there could be other factors affecting it that could make life possible basically on any planet, for all the way from Mercury to even Pluto or some other, like, or asteroids. So by our definition, I think no, but by other definitions, there could be.
Thank you so much, team, for that wonderful presentation. Next, we have Team Rocketry coming up with their propulsion skills and sending payloads off to the sky. So I request Team Rocketry to go ahead with their presentation.
Is someone keeping a watch on the time?
Yes, sir. We apologize that the Q&A session in the previous session exceeded the time limit, but yes, we are keeping the watch.
May I begin?
Yes, you are good to go.
A very good morning to everyone present here and fellow cohort members. It is our pleasure to be presenting our final project, the Hyperion 1, the experimental rocket we crafted over the weeks of this awesome program. We have put a lot of effort into making this rocket. We hope you all enjoy listening to this. Without further ado, let's begin. Starting off, we have our incredible team led by our super cool mentors Mahesh sir and Lakshay sir. We thank them for all the guidance and support. Over the course of the program, we divided into subsystems teams, which are as follows. We divided into structural systems design team, propulsion systems design team, recovery systems design team. In the structural systems team, we have Yash, myself, Kashika, and Angelika. In the propulsion systems team, we have Satyam, Tanmay, and Amog. In the recovery systems team, we have Bharati, Suhani, Ishita, Aryan, and Nishant. These are the main topics we will discuss today. Mission statement, high power rocketry, design of the rocket, subsystems, and at the end, a Q&A session. Our mission statement is to design an experimental rocket that flies to an altitude of 10 kilometers and will carry a payload of 500 grams. What is a rocket? A rocket is a vehicle that is used for transportation. It uses the law of conservation of momentum for propulsion. Our mentors taught about these laws descriptively in the first few weeks of the program. Next, we have high power rocketry by Aryan. Over to you, Aryan.
I'm Aryan and I'm going to be talking about high power rocketry. Unlike the model hobby rockets, experimental rockets use components which are built from scratch. The high power rockets, which are similar to experimental rockets, use rocket motors which are available commercially. Due to the lack of rules and regulatory bodies in India, experimental rocket or rocketry is quite a challenge. The experimental rocketry is advantageous in getting hands-on experience of building rockets that can reach higher altitudes. Rocket motors, which exceed model rocketry motor definitions, and the models that use these motors are collectively referred to as high power rocketry, short form HPR. HPR is similar to model rocketry with differences that include the propulsion power and weight increase of the model. They use motors in ranges over G power or way more than laws and regulations allow for unrestricted model rockets. Rules for making a rocket. A rocket exceeds the definition of a model rocket under NFPA 1122 and becomes a high power rocket under NFPA 1127 if it uses the motor with more than 160 Newton seconds of total impulse. The other rules are given here. Over to Amog.
Thanks, Aryan. Hey everybody, I will be explaining about the open rocket design. This model is in accordance with our mission statement as it is capable of going up to an altitude of 10 kilometers. Here is the 3D finished model of the rocket. Moving ahead, this is the simulation of the rocket, which gives us very important values like altitude, vertical velocity, vertical acceleration, which were used by the structural team to design it in CAD. Over to you, Yash.
Hello, everyone. I am from the structural team, and I will talk about the structure we built. So we basically designed the anatomy of our rocket, and this is the initial design which we built, named it as Hyperion 1. This was built using a software called SCAD software on chip, which is very collaborative. So these are the basic parts which we are going to use in our rocket. First is the nose cone. The nose cone plays a vital role in our during the journey. Due to its aerodynamic shape, it helps the rocket to prevent air friction from slowing the rocket. Next are the fins. The fins help us to guide the rocket fly straight. The fins, speaking about fins, it helps to control the rocket. Next are the body tube. Body tube forms the main body of our rocket, and which connects the nose cone from the top and the fins at the bottom. Next is the tube coupler. The tube coupler joins the two body tube together and strengthen the rocket. Over to you, Satyam.
All right, sorry, due to technical difficulties, I'll be continuing Satyam's part. So I'm here on behalf of the propulsion team to tell what all we have learned and how we applied that knowledge to make our rocket engine. We're using a solid rocket engine because it is mostly used in an experimental rocket and it is easy to design. Since commercial rocket engines are not available for sale in India, we had to design our own engine from scratch. And to design our engine, we used the Open Rocket tool. So there are three main components of our engine. Starting off with the motor casing, it acts like a pressure vessel or combustion chamber, you could say, for a solid rocket engine. It also acts like a propellant tank where it stores the solid propellant in form of fuel grains. Second is the bulkhead. It seals the motor casing so that the gases exit from one side only. It houses the igniter, which is responsible for the beginning of the combustion in the engine. The bulkhead's outer curved surface area is polished and it is attached to the motor, causing by hammering 8 screws. Next is the O-ring, which is a rubber ring which seals the gaps in the bulkhead. There are 2 O-rings present to provide more redundancy. Third one is the nozzle. It accelerates the gases coming out of the combustion chamber, thus providing more thrust for liftoff. Throat is a small cross-sectional area present between convergent and divergent sections of the nozzle. The nozzle is attached to the motor casing by hammering 8 screws. The O-rings in the nozzle also serve the same purpose as they serve in the bulkhead. Now for the propellant, we are using APCP, otherwise known as ammonium perchlorate composite propellant, which uses aluminum powder as fuel. Ammonium perchlorate as oxidizer and HTBP as binder. In the slide is given the physical properties of APCP. Also, we are using a tubular grain profile because it provides progressive thrust time curve. In this table that you see on the slide, the specifications of the engine we have designed are given. It contains all the assumed and calculated values of the physical quantities which we are required to have while designing the engine. Thank you, and over to Sahani.
Hi everyone, I will be explaining the electronics and the basic recovery of the rocket. So what is recovery? Recovery is the process of getting back to the object's original state. In this case, recovery means to regain the rocket after it has reached the ground. Why do we need recovery? Well, we need recovery so that we don't have to remake the entire rocket, but with just a few modifications, use it again, such as replace the engine and refill the fuel, and voila, your rocket can be used again. The electronics we will be using in our rocket are 2 altimeters and the flight computer. The flight computer is going to be used for taking updates from the rocket, such as the altitude, fuel capacity, temperature, and it's also going to be used to launch the rocket and deploy the parachutes. The electronic deployment system has commands that are set prior to the launch of the rocket. When the rocket reaches the apogee, the chip will deploy the drogue chute first. And after reaching the average of 500 to 700 feet, it will deploy the main chute. Over to you, Bharati.
The most popular parachutes used for rocket recovery is the cruciform chute that's shaped like a cross, flat sheet chutes that deployed from the top of the flight, and the panel chute and the elliptical and spherical chute. Each shape has its own advantages and disadvantages. The important thing we look for in the shape is if it suits our rocket's mass and the shape's stability at apogee, and the materials were chosen carefully too. We are using the cruciform chute as a main chute, the elliptical chute as a drogue chute due to its protective frontal area and good stability. There are three ways of packing the parachute inside the body tube: the traditional fold and wrap, the deployment bag, and the pressure pack. The traditional fold and wrap is the most common method used by most rocketeers for its simplicity. Deployment bag used is for the larger chutes, where it is fitted inside a tight space. By following a simple technique, it is easy to get a consistent packing density and a reliable deployment without tangles. The pressure pack is the most extreme method of packing a chute as it has by far the highest packing density. The military and many aerospace deployment systems use this. The three most used ways of deploying the parachute is the black powder ejection system, the CO2 ejection system, and the integrated system. The black powder is easy and reliable, but sometimes the heat can damage the fragile nylon canopies, due to which we use ripstop nylon canopies. CO2 systems is clean and reliable. It doesn't damage your parachute and it can be used at high altitudes, but it has to be designed carefully because of the pressure that has to be managed. Integrated system is very compact and highly reliable. It needs special equipment to pack the chute. Over to Nishant.
Hello everyone, let's get into the specifications of the parachute. The drogue chute and the main chute both are made up of ripstop nylon. We choose ripstop nylon because it is strong and even if there is a hole in the parachute, it won't expand. The shape of the drogue chute is elliptical and the main chute is cruciform in shape. These shapes are the most preferred as they provide more surface area and reduce the descent velocity. We calculated the diameter and surface area of the parachute according to the mass of the rocket and descent velocity of the rocket. The descent velocity of the rocket is 5 meters per second. The surface area of the main chute is 6.79 square meters, and the surface area of the drogue chute is 5.26 square meters. The mass of the drogue chute is 60 grams, and the main chute weighs 396 grams. The packing volume is the area occupied by the parachute when it is packed inside the rocket's body tube. The packing volume of the drogue chute is 158.4 cubic centimeter, and the main chute is 1070.3 cubic centimeters. The hole in the drogue chute is called spill hole. It stabilizes the rocket while descending. Over to Ishita.
Black powder ejection system is used to eject both the parachute. At the apogee, the drogue chute is deployed as a result of the ignition of the black powder, also called the gunpowder. At an optimum altitude, the main chute is deployed in the same way. The black powder is stored in a small metallic tubes attached to the coupler, which also has an e-match or an igniter attached to the flight computer. The burning of the black powder produces immense pressure to deploy the parachute. The amount of black powder required as per our calculations are 1.48 grams for the drogue chute and 3.42 grams for the main chute. These are the parachute and ejection charge we are using in our rocket. Over to you, Fida.
Thank you, Ishita, for the wonderful explanation. This is our final rocket model. The pictures you have seen before was the initial design. Later, we decided to go with dual deployment. What's next? The team is planning to take this project further and maybe hold a crowdfunding, get all the parts for the rocket, and then assemble it. For the time being, we have placed a dummy mass for the payload, but we plan on replacing it later with a scientific tool or something as such. With that, we have come to the end of our presentation. I hope you all enjoyed our presentation. Now we have the Q&A session. If you have any questions you would like to ask, please post them in the link posted in the chat. Thank you.
Thank you, team. That was an amazing presentation, and we are good to go ahead with the Q&A session. The link for the Q&A session is posted in the chat again. So I request everyone to post your questions on this link, and the questions will be presented on the screen.
Hey everyone, it's me. I will moderate the questions.
So we have a question coming up from Margarita Mom.
Tejas, could you also read out the question while it comes in?
Yes, great. Okay. Team, Margarita Mom's question is as follows. Chemical propulsion is extremely inefficient because most of the low payload mass fraction, most of the mass in it being fuel, somewhere close to 80 to 90%. What other methods of launching to space do you know? That, of course, only theoretical for the future. Okay. So Mom wants to know about the other propulsion methods which are futuristic and conveniently carry a lesser fuel mass.
Okay, as of now, we're not really sure about the question. We'll research on it and get back to you, ma'am.
I'm sure, for example, you must have heard about space elevator idea. Or electromagnetic or railgun, electromagnetic launcher.
The propulsion, anybody from the propulsion team could take the question up? Because I was...
Yes, ma'am, we have heard about them. But
yeah, this is not exactly propulsion, it's just other methods of launching to space. Railgun, electromagnetic launcher, or space elevator, or even laser, like pushing with the laser. You can read about it because chemical propulsion is really extremely inefficient, yes. And even, for example, the payload mass fraction of launching to the space shuttle, the actual payload is only 1%. Payload means astronauts or equipment. The rest of the mass is, most of it is in the fuel.
Yes,
that's called the tyranny. That's called the tyranny of the rocket equation. You can look on the there's a nice article written about it. It's called the tyranny of the rocket equation. Just look at it on Google. You'll have fun reading it.
All right, ma'am. We'll research more on it. Thank you for the suggestion, ma'am. We'll definitely look at it. And sorry for not answering your question. We're not really that aware. That's why.
It's a point to learn, team. So yes, now you're aware of your pitfall. So we have the next question by Narhari sir. So he wants to know whether the system that you have designed is it a single stage system.
Sir, I would like to take up the question. I work in the structural team, and no, it's not. It is a single stage rocket. It is not a two-stage rocket. We just have two body tubes which you have connected with a tube coupler. I hope that answers your question.
Okay. So we have another question from Kiran Mai. She wants to know how did you calculate the mass and the packing volume? I guess this is being addressed with respect to the payload system.
The payloads, I did address that the payload will be a dummy mass for the time being, and then later on we'll be shifting to a scientific tool or something as such. So it's a dummy mass as of now. And the 500 gram, it was a constraint given to us. So that's basically our mission statement.
Okay. And just another question. This is an anonymous question. In the recovery, if the parachute breaks, what alternative you have to prevent any damage to people or objects on Earth?
I'd like to take up this question. So basically, our parachute. So basically, we have programmed the flight computer as such that suppose the drogue chute is stuck at the apogee, it is programmed to deploy the other main chute. And suppose so basically, we have these alternatives that are there, and we're still working on more. Does that answer your question?
I hope it did. Thank you so much, team, for answering all the questions. There are a few more questions which I'll be forwarding it to you all personally. Due to time crunch that we have right now, we'll be proceeding with the next team. Thank you so much, team.
I have one or two suggestions to the team. I'm Sudhir.
Yes, sir.
See, first of all, making the understanding, please have complete understanding. I hope the mentors will. When you say 10 kilometers altitude and you are talking about apogee and perigee, okay, 10 kilometers altitude, really no satellite will take a orbit, okay, that is, it's almost like a plane flying, okay. Please read more text on that one. Then you are talking about the solid propellant and it doesn't have any bulkhead, it doesn't have any propellant tanks, okay. Your statements are not commensurate to the technology that you have adopted. Please read through good text. Okay, when you are making the statements, the structure, as he said, when you are designing the structure, the payload mass versus the structural load you have to carry. It is not just making a pipe and making fins when you see the let us say literature images in the Google. Okay, when you are making really rocket design is not so simple. Okay, for your level this understanding is enough. Please go through the literature in a more specified way, because at least when you are making the statements you should not commit mistakes. Solid propellant tanks, that is one mistake. Bulkhead, that is another mistake. Okay, couplers will not work here, because when you are joining the two stages, couplers will not work. O-rings you are telling to the nozzle, okay, fine, O-rings will be the nozzle really may not mean the O-rings, because nozzle should have a different kind of mechanism to attach to the. Please read through, because I can appreciate your effort. Please go through the concepts more vigorously and read through.
Yes, sir. Thank you, sir, for the suggestion. It was an experimental rocket.
No,
That's
whatever
why.
the experimental racket, you cannot fiddle with the technologies.
Yeah.
Propellant tanks is for the liquid rockets, not for the solid rockets. Bulkhead for the oxygen tank and a fuel tank, the bulkhead will be used. Okay. When you are making such statements, no, please be careful. Okay.
Yes, sir. Thank you for the suggestion.
Thank you so much, sir. So I hope the team takes it as a input and work on their
Yes.
future project, continue taking up this project and realizing it. Thank you so much, team. Next, we have the team satellites, that is Delta Cosmos, who have worked on a Cube satellite project. So I request Nidhi to present her screen and go ahead with Delta Cosmos presentation.
Thank you. Good morning, everyone. We welcome you all to Team Delta Cosmos, the satellite team. Our objective was to take a space selfie at the zenith. You might be wondering, how is that done? What does it mean? Well, behold, while we take you through the entire process. To make sense of this project, we had two amazing mentors to supervise us, Sujay sir and Aditya sir. As most teams have leaders, we have them too. I'm Nidhi Mayurika and I'm the team leader and the moderator of this presentation. Farida here is our international friend, as well as one of the youngest in our team, who's also our associate leader. Now, this is our dedicated team who have worked so hard on this project while managing schoolwork and personal work parallelly. I'd like to call upon all of you to introduce yourself now.
Hi, I'm Manya Manjunatha from Keli Society School in Bangalore. I work in the app team and the sponsorship team.
Hi, I'm Sachit. I'm in the app team and I'm from Mumbai.
I'm
Hello all, I'm Vahini from Shivamogga, Karnataka from Kasturba Girls PU College. I'm working in sponsorship and design team and camera system specialization.
Shwetang, would you like to go ahead?
Yeah, I'm Shwetang. I'm from Nasik and I'm in the app development team.
We have Vedant also here, who's from Bangalore. We have Spandan, who's from Bangalore.
And hi everyone, I'm Garangi from Ghaziabad and I'm working with camera systems specialization and with design team and also with documentation team.
Thank you, everyone. So to make our work more efficient, we divided ourselves into several other teams. First, we have our design team with Spandan and Vahini, app team with Farida, Manya, Shwetang, and Sachit, sponsorship team with Vahini, Manya, and myself, documentation team with Farida and Gaurangi, payload team with Vedant, Spandan, Gaurangi, and Vahini. Now, for the moment we have all been waiting for, welcome to the design team. We have Spandan, Vahini, Gaurangi, and Vedant. They have worked on the design and components of the satellite. Well, now I would like to take the opportunity to warn you all and advise you to wear your seatbelts and brace for impact, because now you're going to be bombarded with terms you have never heard before and drawings that you believe you have only seen in movies. So now I welcome the design team. Please take your launch.
Thank you, Nidhi. Hey everyone, this is design team over here. So we have worked upon the 6 major subsystems that we'll be needing for our CubeSat and also the 3D designing of our CubeSat. So first comes the optical payload, that is the imaging system. So it is the most integral part for our CubeSat. Then we would be needing a camera module that will fit in our 3U CubeSat and that will be covering the maximum area of 2U that reflects 2 units. For the lenses, we are going to use spatial resolution imaging with 500 mm of optics mirror lens, and that will help interdimensional magnification from polar orbit. For a single image, the user will be able to view a very adequate ground area. Next, if we come to our onboard data handling system, so it is ICEPS offered by EXA, that is potential for now, but it is worked as a central heart for our CubeSat that will enable our model to use higher performance hardware and features. It comprises of many single cards of 25 mm thickness. Now, if we come to our power system, so we are going to use solar panels. That is the only major energy source in space for our CubeSat. Now, we are going to use triple junction technology for that, and that will help us to the maximization of solar into electricity input. Now, we are going to use 3 layers of solar layers in our each solar panels. There will be 8 solar panels, 4 and 4 at both the ends, but still we are debating on it, and that will be opening like a cross. We are also going to use hinges for it that will increase the surface area for our satellite. And if we come to the framework of our satellite, so we are going to use aluminium 6061-T6 and aluminium 7075 alloys. That is why we are using it. So it is aluminium 6061-T6 and aluminium 7075 alloy due to they have low thermal coefficient that is essential for every satellite to send up into the space to prevent cracks and structural deformation that is caused due to the wide temperature ranges. So we are also uses batteries and that will help our satellite to work more efficiently. Now, I would like to call upon Vedant to discuss about other 3 subsystems.
So hello there, I'm Vedant, and I'm going to talk about the other 3 subsystems of a satellite. So for communication to and from a satellite, we'll be using an S-band transceiver made by SatLabs. This can pick up a frequency of 2 GHz to 4 GHz and is commonly used in CubeSat systems like the one which we're working on. Then moving on to the ADCS or Attitude Determination Control System, we'll be using magnetockers and reaction wheels to reorient our satellite. And for the structure and thermals, which will provide structural integrity and thermal protection to our satellite, As Gaurangi stated, we'll be using aluminum alloys such as aluminum 6061T6 and aluminum 7075. Hand over to Vahini for the redesign of the satellite.
Thank you, Vedant. And yeah, so this is our base design. Based on this, we have worked on the 3D model and we are going to be working on our real satellite. It consists of 3 compartments, as the name suggests, 3 human 3 units, which consists inner components. So this is our base. Next, now we can take a brief on orbit on which our satellite is to be placed. So our designated orbit is polar orbit. Polar orbit take the satellites over the Earth poles. Satellites with polar orbits are used for monitoring the weather, taking images of Earth's surface, as well as remote sensing applications for surface mapping. Since our satellites need to take snaps of any part of the Earth's surface, polar orbit is best suited. Our satellite could travel at speed up to 8 kilometers per second due to lower orbit altitudes around 200 to 500 kilometers. And now is the time you all been waiting for, and that is the journey to the 3D world. So Spandan and me are ready to take you on. Go on, Spandan.
Yes, so hey, I'm Spandan. I've been working on the 3D model of the 3U CubeSat. So as you can see, the first main components of the CubeSat is the camera module. It will be occupying the space of about 1.5U to 2U. It consists of lens, sensor, teleconverter, and a configuration board. Yeah, next is the ICEPS spacecraft system core that is going to be the potential ODHS of our CubeSat. Next up, we also have the battery packs that are the dual-layered high-density LiPo battery array. There are 7 volts and 12,000 milliamp hour. We also have the S-band transceiver from SatLabs that handles the communications array of our entire CubeSat. Part of the ADCS, we have the magnetokers. There are 3 individual ones on 3 axes, which use magnetic flux to reorient the CubeSat. Also part of the ADCS, we have the reaction wheels. There are 3 individual brushless motor wheels used to position the CubeSat on 3 axes. To control each one of the components of the ADCS, we have the ADCS control board to link the reaction wheels and the magnetokers. We can use a Raspberry Pi board or Arduino boards for this. Next, we also have the sun sensors placed on all 5 sides of the CubeSat that are used to find out about the apparent position of the CubeSat. This is the vertical section view and also the exploded view to know more about each component separately. I finally pass on the mic to Vahini again to show us the 3D structure of the outer body.
So this is a 3D model of the outer structure of a 3U CubeSat. It consists of solar panels, which are the power sources of our satellite, and we need to mathematically calculate exactly the power sources and power budget of the cube satellite. Adding to it, we need additional time to decide also some components within our CubeSat to how many solar panels we need to use, whether 8, 4 on one side and the other 4 on the other side, or just 4 on the one side. And the cuboid you're seeing will be outer protection for the inner components, and it would be made of aluminum 7075 or 6061T6 alloy, and our optical payload will be protruding out. So this is about the design of our satellite.
Now, this does look like it has been taken from a movie, but guess what? No, this has all been done by our design team. They have worked on this for the past 2 weeks. So if you need a new designer, well, you're looking at their portfolio now. They're ready to be hired. Now that we have our graphic designers, I'd like to introduce you to our tech experts, our app team. Do you want to access satellite images? Do you want to feel more connected to satellites? Well, we have the solution. Satellite Snaps is here for you. Access images from space, take pictures of different locations from a satellite view, and learn more about satellite imaging. With space tourism being so costly, we are here for you to feel more connected by giving you a virtual experience. Play exciting games and learn more. This app is for all of you space nerds because become even more interested about space with our app Satellite Snaps. I now welcome our app team with Farida, Manya, Sachit, and Shwetang to explain more about this amazing app.
Thank you, Nidhi. Now let's learn more about the app. Our app, Satellite Snaps, is aiming to mimic the experience of traveling to space on a budget by taking selfies. In our app, you can have the opportunity to engage with others all around the world while connecting with Earth and outer space. Additionally, our app raises awareness of the serious topic pollution. Our app is called Satellite Snaps when we got inspired by the power of photography on Earth. We decided to call our app Satellite Snaps as the sounds of snaps that are taken by a satellite. To program our app, we chose Java and React Native. We chose Java because it is fast, secure, and reliable, while React Native is smooth and quick in response. React Native is basically a JavaScript-based mobile app framework that allows you to build mobile apps for iOS and Android, using the same code base, which is efficient and fast. So now that's settled in, where would you store the data? That's where the database comes into picture. A database is typically designed so that it is easy to access and store your information safely. We decided to use MongoDB services. Since React Native isn't very flexible with most databases, MongoDB was the most ideal. It is very flexible with React Native as well as AWS, which is our server. But why do we need a server? Because in order to make the communication of the satellite and Earth smooth, we need a server. AWS, which stands for Amazon Web Services, offers database storage options, computer power, content delivery, and networking, among other functionalities to help satellite snaps quickly respond and scale elegantly. To learn more about the features of our app, I now invite my team member Sachin.
Thank you, Frida, for the brilliant explanation. Now, let's move on to the features of our app. We have a main home screen where you can track the satellite relative to your own position. We also have a reminder system where you can get notified when the satellite passes over your own position. We also have a gallery where you can save pictures and share them with your friends on social media. Our app also supports multiple languages such as Mandarin, Arabic, English, Hindi, Spanish, and French. Our app also supports an inbuilt search bar so that you can search up the location of the picture you want to take. For people living in different time zones, our app supports an auto-take feature where the satellite will automatically take the picture and send it to your gallery. If you also want to have a bit of fun with your friends, you can have a contest between them too, trying to guess the location of the picture they've taken. Our app also features a subscription-based service, the details of which will be explained by my team member Shwetan.
Thank you, Sachit, for a wonderful description of the features of our app. I shall now be elaborating on our 3 plans. In the basic plan, which is completely free of cost, in this plan, we can take 5 photos, use many languages, and share photos too. In the Pro plan, we can take up to 30 photos monthly and 2 auto photos. The exclusive premium plan allows unlimited photos, stickers, and 10 times priority access to the satellite. We shall decide on the cost of Pro and Premium plan soon. Over to Manya for the guidance on the user journey.
Thank you, Shwetang. This is the user journey of our app. When we open the app, we get the sign in and sign up page. After signing up, we learn about the terms and conditions of the app. Then we get to the customized profile page where we can customize our profile picture and username. Then we explain about the plans which include basic, pro, and premium as explained by Shwetang. After choosing the plan, we get to the home page. Here we have 5 options: track satellite and take photos, gallery, game, reminder, and leaderboard. In the track satellite option, we can take photos from space. We also have reminders so that we can remind you to take your photos when the satellite is above you. When the photo is clicked, it is directly saved in the gallery. We've also included games and challenges to make it engaging and fun. We can see our scores in the leaderboard and share them on social media. This is the prototype app. This is the welcome page. Here we have 2 options: sign up and log in. While signing up, you're giving your details and access to your location. After logging in successfully, you're directed to the home page. Here we have 3 options: game, track satellite, and gallery. This is our track satellite page. Here we have 2 options: auto take photos and set reminders. We have our auto take photos option so that we can take photos without your manual help. We have also included reminders to take so that we can remind you to take your photos while the satellite is above you. We have also included leaderboards. We have 2 leaderboards, one with your friends and the global leaderboard. We have also added the app, the game, to make it more engaging and fun. This is a profile customization page. Here we can edit your profile picture, the username, and also invite your other friends. We use this page also to log out from the app. This is the gallery. All of the photos which you have taken from the app is saved here, and you can pin your favorite to the top. Now I invite Farida.
Now Data Cosmos has an important message to new users on satellite snaps. We anticipate for the app to be useful in entertainment and educational purposes only. Your privacy is important to us, and that's why we store your valuable data on secure and reliable databases. Also, you have an option to turn on the location only when you want to take a photo to make you even more comfortable. Additionally, we prepare to tell you that this will be a unique opportunity for users all around the world to be able to go into space and enjoying these spectacular views with only a tap on the screen. Have fun.
All these big dreams need some form of funding. So that's why we have a sponsorship team. We have Vahini, Manya, and myself. First off, we developed a plan and we were able to build levels of steps that we wanted to take up. Level 1, we made a list of possible sponsors. Level 2, developed a template for the email that we would like to send it out so that our tasks are much more efficient. Level 3, we made a plan with respect to who's going to connect to whom and many more. Level 4, we began contacting companies and receiving replies from many. Finally, we spoke to a fundraising organization. Fuel a Dream is the organization that was ready to work with us and matched our requirements. And so we have a special news for all of you. We would be able to raise up to 25 lakhs through them. Even though this is still under its development, we would soon start our fundraiser and share links regarding the same soon. For now, we have our fundraiser set up through Razorpay. We will be sharing the link presented on the screen with you all right now. Please do support us however possible. Share the link to as many people as you can. Contribute to this idea with a few fronts. Provide us contacts of whoever can help us with this project, or really, however possible. So we thank Fuel a Dream for this opportunity. We also recognize that we have so many guests present in this presentation. So whoever would like to help us with this project, such as Sudhir sir or anyone, it would be a great help for us if you would like to provide us with any. I'd now like to call upon Vedant to talk about our future plans. I suppose Vedant is having a few technical issues. So under our future plans, we are planning to find more sponsors. We are looking for buying all of our components that were needed, finalizing the documentation, starting to build the real satellite, and finishing the front-end design and start off with the back end of our app and start off with the fundraiser. Now that we are coming to an end, I'd like to thank you all for listening to us patiently. I'd like to take the opportunity to thank SSERD on the behalf of my team for coming up with such an amazing program for us and allowing us to explore more about space. I thank each and every one of you who have helped us put together this project, Dr. J. Chattopadhyaya to help us and guide us, my team, and everyone. We are now open to questions.
Thank you so much, team. So before I proceed to the question and answer session, I would like to highlight that this is one of the teams who are taking their project ahead and implementing it in the near future. They have carried out the initial stage studies right now and are yet to work out the details. And this is a project which will be implemented in another year or a year and a half. So with that, I would like to invite Sudhir sir to give suggestions to the team.
Thank you. It's amazing to get to know such kind of ideas from the kids. See, the idea is ISRO encourages the student satellite development. Okay, understanding about the satellite is one aspect. Realizing the same through either college or industry is another challenge. Okay, and qualifying the systems. First section is some of the components you have missed it. Please read through and get it to the one is thermal system, very important system when you are really going to the 200 to 500 kilometers orbit. The thermal system only disturbs the entire satellite. Please take care of that one. You include it properly after reading it. The second is data management system. See, when you put a camera temporarily when it is going around the world, it has to capture the images and store somewhere on board. And when it comes to your visible region, then the transceivers will get connected to the ground system and download the images, and the temporary memory will be freed for the next slot of an or next lot of images. Okay, that you put it. Okay, these are all the things. CubeSat is one model is available. So as far as opportunities are concerned, you approach some college. Maybe I think you are all 12th class, or what
Yeah,
is
we
the
are from 8th to 12th class.
8th to 12th class. Fine, never mind. Because when once you complete this journey and enter into engineering college, probably I think that should be your aim also. Take the help of the engineering college. There are structured programs available under ISRO for helping the student satellite. We give a lot of equipment, pays for the equipment, and we will allow the students to come and test. Okay, don't depend on the industry, because even if industry does it, is of no use for you. Okay. So this is the suggestion I make, but it's an amazing job. Really, I'm happy to get to know such a kind of beautiful ideas the kids have got. I'm very happy.
Thank you so much, sir. I think it would be really amazing if we get more guidance from you and any form of support. And also with respect to some of the components, I think it was because we had only 1 month, and this is the initial stages. So that's why we were still
You will get
learning.
it. When you have will, you will win.
Sure. Thank you so much, sir.
Okay, with that, let's proceed to the question and answer session. Thank you so much, sir. So,
This was a fantastic project. I think I am amazed at the 360 degrees view, right from the basic conceptual design up to app and the entire thing. I was really amazed. I think the kids have done a fantastic job.
Thank you so much, sir. It means a lot to us.
thank you so much, Ramabu, sir. Okay, do we have any other guests here addressing the making suggestions to the team before I go ahead with the question and answer session?
So, Ramesh here, we're from space, a private space tech startup. So, whatever you guys have done is very nice, and especially the 3D view that you have done, it's really fantastic. And I'm sure you guys had a very good learning while planning for it and then while planning the whole structure. And so I wish you all the best. And as sir had already said, probably by the time you get into engineering, you guys should pursue it. And I'm sure at that time it will become much more affordable. Right now it's costlier, but then by the time you guys enter college, 2, 3, 4 years down the line, it will be much more affordable. So you should pursue it seriously. All the very best, team.
Thank
Yes,
you
sir.
so much, sir. It means a lot to us.
The team is actually working even after this tenure, and they will be realizing this product. So they also have started on the crowdfunding campaign, and which will be initiated very soon. So that being it, thank you all so much, and I'll go ahead with the question answer sessions for the team.
And if any help is required in terms of identifying investors, I've got some contacts with startup angel investors and all. I can help them out.
Sure, sir. That would actually help us a lot. Thank you so much, sir.
So team, here we go ahead with the question answer session. So there is a question by Narhari sir. He wants to know, okay, is the question visible?
No, sir. Yeah, now it is. Yeah.
Altitude needs to be at least 150 kilometer or above for a stable orbit. Anything lower would be unstable. So will the optics be good enough for the altitude for selfie?
Yeah, so we did understand this, and we did try to figure out if whatever lenses we are using is good enough. I think I'd like Spandan from the optics team to answer further.
Yeah. So basically, since 150 kilometers is not enough, we are going to be sending it into the polar orbit about 200 to 500 kilometers above the surface. And also regarding the optic system, we have the lens that's about having the magnification of 500 millimeters. That will, and we also have the teleconverter attached to the lens and the camera, which will efficiently magnify our focal length twice the length. And so we'll be having about 1000 millimeter optics of the focal length. And yeah, I suppose that answers your question, and we will be having a good spatial resolution as well.
Thank you, Spandan.
Thank you so much, team. And next, we have a question from one of our SSERD students, Venkat. He wants to know what does a CubeSat do? What does the CubeSat designed by you do? And how long would it last?
So basically, we want to make this CubeSat wherein it would take pictures of different locations. We are looking for like Farida mentioned in our presentation, we are looking for educating people onto a surface level of what actually goes on with pollution or many of the natural calamities, and we are trying to make it more accessible to the public using our app. And now, because this is more of a public usage, we are trying to see how we could increase the longevity of our app, or our satellite. So we don't want it to be like a 2-hour thing. We want it to be at least more than an year. So because it's going to create that hype for our public to use the app also. I think we would be working on how much time it could stay up, but I think for now this should be the answer.
Thank you, team. There's another question by Dr. Vijay. He wants to know, have you thought of using carbon composites for the structure?
I think, yeah, actually we did. We also thought of we also heard of SpaceX using wood as its outer structure. So we did look into all of these, but we decided upon aluminum, the alloys of aluminum for a particular reason. Vahini, would you like to take this up, or Spandan, or anyone from the payload team?
Yeah. The carbon composites, yeah, we will be looking upon that as well. We'll shine a light about that too. We particularly stick to aluminum alloys because it were one of the most commonly used materials for the structure of the CubeSat, and they were most common in most of the CubeSats actually, and mainly they were used for the lowest thermal coefficients. Aluminum was used because it's light and it will save weight. Carbon composites can be looked upon as well. Yeah, we'll have a bit of research on that as well. Thank you for your suggestion.
But sometimes if the space debris any problem if comes up, so we using wood or any other carbon components would be risk taking. So we thought of using aluminium, which is a bit sufficient for our CubeSat to be last longer. Hope that answers.
Thank you so much, team. That was a wonderful presentation followed by a very good Q&A session. There are actually pretty more questions, like really good questions that I have, but due to the time crunch that we are facing right now, we will not be able to take it, but I'll make sure that the question goes to the team and it gets answered. Thank you all so much. And we'll go ahead with the next team, that is Team Aeronautics. We have Team Project Vimana presenting a conceptual design on an aircraft here. So do we have Team Aeronautics?
Yes,
Yes,
sir.
sir.
I'll be presenting. I hope my screen is visible.
Atlas 90%. Yeah, it's visible.
Okay. Am I audible?
Yeah.
Okay. Good morning to one and all present here today. I, Aditya, and my teammates from the Aeronautics team Project Vimana will take you through the roller coaster of our conceptual designing process. We have 5 subgroups amongst ourselves, which are structure, aerodynamics, propulsion, avionics, cockpit, and ergonomics. Now, our problem statement is to design an electric light sports aircraft specifically for tourism purposes. We started the designing process by estimating the max takeoff weight denoted by W0. Before we start the designing process, we have to know the 4 fundamental forces: lift, weight, thrust, and drag. When lift is equal to weight and thrust is equal to drag, we call it a leveled flight. Over to Ashwita.
The max takeoff weight is broken down into the empty weight, fuel weight, crew weight, and the payload weight.
So basically the max takeoff weight equals empty weight plus fuel weight plus crew weight plus the payload weight. So this is the data that we collected. So we first found the max takeoff weight of 30 different two-seater LSAs, and then took the average of all those weights and got around 580 kgs. We considered each person to be 70 kgs with a luggage weight of 10 kgs. Then we collected the data for different parameters for all those 30 LSAs, and then took the average max takeoff of all those planes. And we firstly got 643 kgs, and then by using multiple iterations, we got 580 kgs as our first max takeoff weight was overestimated. Next slide. This graph shows how we got 580 kgs by using multiple iterations. Over to Anjali.
Hi, I'm Anjali and I'll be talking about the performance requirements for our LSA. We decided on some basic performance requirements by looking at those of other light sports aircrafts and by figuring out what we wanted our plane to be used for. We went with a cruise speed of 60 meters per second at a 3-kilometer altitude with an endurance of over an hour. We decided on takeoff and landing distances of 200 meters as we wanted our plane to be used for tourism and it shouldn't require too much space. Our rate of climb was altered multiple times and brought down to 689 feet per minute so we could lower the thrust to weight ratio. Next slide, please. After setting some basic requirements, we moved on to more detailed ones using the constraint diagram. We found the thrust to weight ratios at different points, the vertical speed or the rate of climb during takeoff and while landing. We used the formulas with the different wing loading values. The wing loading is what is shown as W by S in the formulas. The feasible region from which we could choose our thrust to weight ratio was on the left of the landing constraint, above the other curves. And from this region, we took the lowest thrust to weight possible as 0.21. And we found the wing loading to be around 375 newtons per meter square. Thank you.
So I'm Sarvesh from the structure team. So the structure team decided upon the design and dimensions of the aircraft, that is of fuselage, wing, empennage, and landing gear with the help of inputs from various other subgroups. For the design of the fuselage, we went with the semi-monocoque design that you can see here in the picture. The reason being it provides an internal structure and strength as it has longerons and stringers, unlike monocoque, which has a stressed skin as its main support. Second, it can be molded in a streamlined manner, unlike the early open truss structure, which is rather rigid. Third, even though it is relatively heavier, we can meddle a little with the weight by changing the materials used for the skin. And for landing gear, we are thinking to add 2 wheels at the front and a small wheel at the hind part.
Hi, I'm Rish from the structures team. I'm going to be talking about wing platform design. Wing platform consists of the shape of the wing from the top view. The 3 factors that are very important to understand the wing performance and overall aerodynamic characteristics of a wing are aspect ratio, wing area, taper ratio, and sweep. The aspect ratio is the ratio of wingspan to wing chord, and we've chosen 9 chord. And for the wing area, we've chosen 15 meters square. The taper ratio is a decrease from wing root to winglet in wing chord or wing thickness, but in wing chord, we've chosen 0.85 for the main wing. And our aircraft is forward swept, but only for the trailing edge, which is the frontal slant of the wings, but only for the back. We're going with a high wing configuration so that we can use struts to overcome bending of the wings, as we went with a high wingspan, which is 11.62 meters. We're using wings with a dihedral angle of 2 degrees each as to provide stability. Even if a gust of wind harshly hits the aircraft, making it tilt, the center of gravity will pull the aircraft back to its original position, causing no damage. Because we're using tapered wings, we're going with a root chord length of 1.64 meters and a tip chord length of 1.29 meters. We're going with 9 as our aspect ratio because an increase in aspect ratio with constant velocity will decrease the drag, improving the performance of the wing when in climbing altitude. Although with an increase in aspect ratio, there's also an increase in the wingspan length, causing an increase in the weight of the wing structure, which means the wings would be heavier. Besides the aspect ratio, a way to change the platform is by tapering, which again is decreasing the length of the chord from the root to the tip of the wing. In general, tapering will cause a decrease in drag and an increase in lift, but there's also structural benefit due to the saving of the weight in the wing. So this way the weight gets compromised and it all balances out.
So the empennage is basically the tail, which consists of a vertical fin, horizontal stabilizer, elevators, and rudders. It mainly creates force that acts upon a lever arm to help the plane for pitch movement and yaw movement. So how did we calculate the dimensions of our tail? The first thing that we did was to get the historical data for tail volume ratio for aircraft similar as ours, with which we got our ratio to be 0.7 for horizontal stabilizer and 0.04 for vertical fin from various papers. The formula that you see here is for the tail volume ratio, and the first value that we had frozen from there was of lever arm for both vertical and horizontal stabilizer, which is 75% of fuselage length, that is 4.13 meter. And by computing the values, we found out our area of stabilizers. The next thing that we did was that we looked into the student research papers and found out the trend of aspect ratio and taper ratio for a conventional tail, which helped us get our length of stabilizer. Next slide, please.
Space scientist.
So we thought that an aspect ratio and taper ratio 1.3 and 0.5 for horizontal stabilizer and 3.5 and 0.5 for vertical stabilizer would be good. With this, we got our horizontal stabilizer length and area as 3.38 meter and 3.28 meter square, and the vertical stabilizer length and area as 1.49 meter and 1.7 meter square. Thank you.
I'm sorry, whosoever has done that, can you please remove that annotations? So hello everyone, this is Kushagar from the aerodynamics team. So our team mainly worked to decide which airfoil to be used for our aircraft by comparing the different airfoils that are existing. So how did we do that? We first started with the airfoil requirements. The airfoil requirements were a low-speed airfoil because we are working on a light sports aircraft. Other one was the high lift-to-drag ratio because that would result in greater efficiency. The airfoils we considered were the NACA 4412, NASA NLF, and the Clark Y airfoil. The NASA NLF. So as you can see on the screen, the specs are on the bottom left, and on the bottom right, we have the graph of the CL versus alpha. On analyzing this graph, we get that it has a better lift to drag ratio. It's a thicker airfoil, which makes it a good airfoil for a low speed aircraft, but it has a rapid stall characteristic. The next one is the Clark Y airfoil. On the bottom left corner are the specs of these airfoil, and on the bottom right corner is a CL versus alpha graph of this airfoil. On analyzing this graph, we can see that on analyzing the picture, we can see that it has a flat bottom, which streamlines the angle measurements for the propeller, making it simpler to create the wings. Also, it has smoother stall characteristics if we compare with the NASA NLF. But it is comparatively less thicker than all the considered airfoils. Over to Ashwita.
Next comes the NACA 4412. As you can see from the graph, there's good lift to drag ratio and better lift even at a lower Reynolds number, as the blue line almost overlaps the orange line. Next slide. So we chose the final airfoil to be NACA 4412 as it has a better stall behavior, a good lift to drag ratio, as well as a greater stall angle. As you can see from the graph, that the gray line has a smoother curve.
I call upon Srilasya from the propulsion team.
Hello, I'm Srilasya from the propulsion team, and our main aim was to design an electric propulsion system for our aircraft. So what me and Anjali worked on till now is first we started by estimating the battery weight, because in an electric aircraft, unlike conventional fuel aircrafts, the battery weight won't change throughout the flight. It'll remain the same, and it'll be part of the empty weight. So we referred to planes with similar MTOW, or maximum takeoff weight specifications, planes like Pipistrel Alpha Electro, and we used its battery weight to come up with the average battery weight of ours. That's 122 kgs. So our battery weight was 120 kgs average. So Also, we also had to find the motor requirements for our aircraft in order to satisfy the thrust requirements. So our max power output has to be 90 kilowatts, our continuous power output has to be 75 to 85 kilowatts, and our rotations per minute or RPM has to be 1500 to 4000 rotations per minute. Next, our propeller details. So for our propeller, we decided to go with a 3-bladed configuration that has 1.625 meters in diameter. We got these values by referring to more planes with similar specifications like electric LSAs that require the same amount of thrust. Then we had to use a graph in order to find our propeller efficiency and pitch angle of the propeller. So what a pitch angle basically is it's the angle between the chord length and the plane of rotation. So as you can see the graph, it's a graph which has propeller efficiency versus the advance ratio. The advance ratio is J, which is equal to cruise velocity upon n into D. N is the rotations per second and D is the propeller diameter. So we had to find J1 and J2, and on those curves, we had to find the maximum value of the propeller efficiency. Therefore, we got 0.84 as our propeller efficiency. And as you can see, each curve represents a certain pitch angle. So we took 20 degrees as our pitch angle because our propeller efficiency also falls upon there. And it's in between our J values. So that's how we got our pitch angle and a propeller efficiency. Lastly, we also looked into the general working of a battery management system or a BMS and how it basically works. So it's connected to the batteries and it helps give the pilot updates on the battery health and the charge remaining. We also looked into the PDS or the power distribution system, which helps distribute power from the battery to the motor by receiving inputs from the throttle stick in order to generate adequate thrust from the propeller. So this is what we've done till now. And next we have to look into battery management system like in depth and the battery configuration. We also made quite a few mistakes with the motors and the requirements, which is why it took so long. But in the end, we went with a custom motor to fit our design. Thank you.
Good morning, everyone. I'm Nikhil. Avionics is a vital system that allows pilots to control the plane. Now, Aditya will say about the instruments used in this LSE.
We will be using 3 vital controls in our aircraft as we are making a low-speed aircraft, which are speed indicator to tell us at what speed we are going, vertical speed indicator to tell us whether we are how much we are ascending or descending, and our altimeter to keep a track of our altitude. Next, we will need a pitot tube in order to get the data for the above 3 instruments, which is for which the air has to enter through the tube. And the data, once the data readings which we need is gotten, the drain hole in the same system will remove the air and then to avoid any clumsing, we will be placing our pitot tube under the wing. Thank you.
This LSA will use the GPS system for aircraft as the navigation system. We are choosing GPS as our LSA navigation system because our LSA will be an international product and GPS is available internationally. For first, we will use the Gagan navigational system and afterwards, when our aircraft is in demand, we will also make the GPS variant. Thanks.
Hello everyone, I am Sneha Munshi from the Cockpit and Ergonomics team, and I'll be updating you all about our work. So as you can see, these are the dimensions of the cockpit that we found out after researching. And these are the different views of the pilot under 2020 vision. So basically, I'm going to explain all these views. So max upward view is the maximum upward view that the pilot can see without moving their head or straining their eyes. And the max downward view is just its opposite. And the horizontal line is basically when you see straight. And then you can also see the angle of the seat should be 60-degree vertically. Over to you, Sneha.
Hi, I'm Sneha Kaur from the cockpit design. So we have found basically that how the seats are to be made. Seats are to be made with aluminium foil and block of polyethylene film attached to it, and a layer of cloth or leather. And also we have found the dimensions of the cockpit, where the pilot and his co-pilot will sit. The length of the cockpit seat is 16.5 inches, and the height of the seat is 20 inches. The length of the seat from the base is 10 inches, and distance between the instrument panel and seat is 20.5 inches, so that the pilot will not have to move, and he or she can basically do it without any difficulty.
Next slide, please. So for the gratitude, I would like to thank Dr. H.K. Narahari for his guidance and support. And we are thankful for our friends and family for constantly supporting us. We would like to heartily thank Nikita ma'am and Sujasa and the whole team of SSERD for providing us with this great opportunity. And we would also like to congratulate our team and ourselves for accomplishing this dream and what seemed like a mission impossible. Thank you, everyone, and we are open to your questions. You can post your questions.
Thank you so much, team. That was a wonderful presentation. We have Vaibhav here with us from Aviakul. So, Vaibhav, can we have your views on this project?
Yes, are you able to hear me?
Yes, Vaibhav.
Okay, so first of all, it was a wonderful project, right? And since I'm majorly from this background, just to give a little intro, so I'm myself an aeronautical engineer, and I have been in Moscow for a long time. I just came back to India, right? So I could see that back there are a lot of experimental projects, and I was always complaining that I don't see much of that in India. But I'm so happy that after long I could see students designing and they conceptualizing this electric flight. So yes, I like the idea that they divided the whole work in terms of what it is actually being done like in real life, so that you actually have an economics department, you have a wing department, you have stabilizer department, and so forth. So that teamwork is much appreciated. And in terms of specifications for their level, for their because I'm not sure what is the educational background of the students. I don't have the idea whether they are college students or school students. Can you please let me know?
They are grade 8 to grade 12. So they have a grade 8 to grade 12.
Wonderful. Then it's beyond my expectation. That's one, because I do have a lot of college interns who, by the way, don't understand most of the terms that they have spoken here. Okay, so it's good that they have a clear understanding of what seats need to be there and what kind of wing design needs to be there. So it was really great, really great. And I wish them all the luck. If they do have any further inquiries or they need any other guidance, I'm always open to them. I think Nikita has all my contacts. Thank you for inviting me, by the way. I thoroughly enjoyed the presentation. And so you can take my contact from her if you need anything in terms of aviation, if you need to connect to laboratories where you can actually realize it. So we do have a working lab back in Delhi where we support the experimental prototypes. So if any of these students want to come up and they want to design, actually see how their design works in real life, I would be more than happy to take them.
This is also one of the projects, along with the satellites team, that is being pushed in for realizing. So this
that's great.
This will not.
So I was not present during the satellite one since I was otherwise engaged in the morning. I just happened to be in time for the aeronautics because that's where I'm really specialized in. But yeah, having all said and done, you can always ask the satellite team also to contact me, and I will try my best to get their projects funded, because we work in the commercial sector, so we do hang around a lot of investors and other people. So we'll try to get their project funded, but before that, we will try to realize it in the small scale lab at least. That's what we can do. Yeah.
Thank you so much, Vaibhav. I also have Narahari, Dr. Narahari with us. So he has also been with us during one of the intermediate presentations as well. So we would like to take his view.
Tejas, you want me to say something?
Yes, sir.
As I said, it's a brilliant work, and I wish my own students do this kind of work, this amount of work. So it's really, really amazing for school children. I wouldn't say children because they have grown up mentally. From this presentation, I see they're as good as, at least a third or fourth semester BTech students. So it's pretty good work. And I wish them all well. So, excellent work. So for all the teams have done very, very well.
Thank you so much.
Thanks for inviting me. Thanks for inviting me.
Thank you, sir. So we have, Shashidhar sir. Yes, sir. I'm very much excited to hear from you.
Yes, it's an excellent team and a lot of talent, right from all aspects of the thought process. And of course, the presentation skills are great. Actually, in Rotary, we are having a program called AK EduSat, Abdul Kalam Educational Satellite Program. This is fulfilling the dreams of Abdul Kalam, so as to provide knowledge connectivity or bandwidth to each and every nook and corner of the country. Nobody should be deficit of bandwidth. He had thought about that, a number of years ago. Under the Pura, providing urban amenities in rural areas. That was his dream. Now, in this Rotary, what we have done is we want to develop nano satellites and launch them into space in cooperation with ISRO. And we are looking for teams of people who can make it happen. We can arrange for grants from international sources and Rotary International Literacy Mission. One of the dreams of Rotary is to make India literate by 2025. So we have a lot of funds there. We have a lot of ability to get global grants. This is called global grants from foreign Rotary foundations. So we have, there is no fund shortage for any of your projects. If you align with education sector, so you say I'll deliver to education content. So we'll take you through stages. Of course, SSERD is part of that program. We will discuss it further. So let us work together, SSERD and Rotary International. Thank you.
Thank you so much, sir. Sudhir sir, if you can add your views on this work.
I can only tell probably I think Boeing people, if they listen to these people without looking at their faces, probably they may get misguided. Some competitors are coming up. Okay, there's only one word I can say. Kids, you are doing amazing job. Please continue, because this is one area where your exposure itself is a very great achievement. Okay, please get to know something more practical things. That's all I can tell you. Get to know something more practical aspects and do with a small experiment. Okay, it's maybe a kite. Don't talk about battery management, because I am part of the national committee for making the batteries for our ADA and other things. Okay, never mind, because when you talk, I accept it. Please get to know something more. I think Nikita, these girls and boys, they will help you. Get to know something more, do some more research, and a little bit come close to the practical. I think Mr. Shashidhar has assured you to fund it through lot of agencies are there. ISRO is with you all people. I wanted to make some more programs like this. Probably let me see with this enthusiasm. That's the reason I just made myself available to listen to you. Let us see how best we can penetrate into the education. All the best, kids.
Thank you so much.
Thank you so much, all of us, sir, for your feedback. Sudhir sir, thank you so much for being here. So this is for all of you. This is actually an online program, so we had its own limitations on how much they could spend. And one more thing I think I should mention here is that the students had a time limit of like 3 hours a day or so, which they could work. To only towards the end they were spending more time on working and understanding different aspects of it. So I think there is that that also as a drawback added to us in this particular stage. Hopefully, as we run this on a long-term basis, we can solve all that issue. And yeah, so Shashidhar sir, definitely we will reach out to you. We'll see how we can, proceed, work together, and have these projects come to life. And also, Sudhir sir, I want to request you on the stage in front of all the students. We want ISRO to also support us on the projects what we are doing. Hopefully, you can do that. I know that all of you are in a position to help us in a lot of different ways. So I request you also to help us in any possible way on any of the projects. Any projects you pick, you want to help us, please.
Definitely, we'll look into it. Definitely.
You guys can tell the Rocketry team to get in touch with me. I could probably help them with the components. I think we have available everything that they need. They can build out their whole thing.
That's amazing, Divyanshu.
Oh, Divyanshu is here. You just pull him. He will help you a lot. Good.
Thank you so much, everyone. Do we have Margarita ma'am with us saying a few words about the team?
Yes. Oh. Yes, hello. Yes, it was extremely interesting to listen to all the teams. Of course, technical teams, it's not exactly my area of expertise, but satellite team, it's like really amazing. I had some questions, but there was quite little time. Well, we can always be in touch, and as far as I understand, the teams are still working on their projects. It's not that they complete. Anyway, science is a continuous process. So thank you for inviting me for this.
Okay, we can quickly take 2 questions. So we have the screen being shared for the questions.
So while he is presenting the screen, thank you, Margarita ma'am, and also Vaibhav, Divyanshu, all of you joining and giving your feedback, and we are looking forward to working with you, all of you. Again.
So we have a question by Venkat Shah. So he wants to know.
So we can't see the question.
What's the main purpose of Project Vimana other than to?
Shall I take the question?
Yeah, sure.
Our conceptual design light sports aircraft is mainly targeted for tourism. Other than that, it can be used for flying short distances here and there. And that is basically the main purpose of the aircraft.
There is also another question wherein they want to know what is 4412 and NACA stand for.
Aerodynamics team, would you like to answer?
Yeah, I'll answer that. So basically, the first digit tells the location, the camber percentage, and the second digit tells the location of the maximum camber in tens of chord, and the last 2 digits tell the percentage, the thickness percentage. I hope that answered.
Okay.
Just to add to it, so it says 4% camber at 40% chord length and 12% thickness. So this is what it means.
Yes.
Thank you, team. So with that, we are good to go ahead with the next team. Thank you all so much for that wonderful presentation. Next, we have Team Valerie, which has come up with a conceptual design for a space settlement. And this team also has been working on this project for a very long time, and they had amazing inputs being placed in for their design. So without further ado, I invite Team Valerie to go ahead with the presentation.
Thank you, sir. I'll be presenting. So you have to enable the screen share.
So good morning to one and all present here. I am Dakshin Viswanathan, leader of Team Valerie, and we are the Team Valerie who are working on the space settlement. So this settlement is like a second home to us. It's like the home for all of humanity in the future. So welcome to the tour of our home.
So now,
Hello everyone, I'm Kritik. Hello everyone, I'm Kritik, Valerie's assistant team leader, and this is our logo. Valerie means strong, brave, and fierce.
let's start off our day with the quote. The time was fast approaching when Earth, like all mothers, must say farewell to her children, by Arthur C. Clarke.
We were led by two amazing supervisors, Manisha ma'am and Deepthi ma'am. And now let me introduce you to the team. Dakshin is our team leader and Kritik is our assistant team leader. And this is the rest of the team. Now the question arises, what is a space settlement? A space settlement is basically a home in space. It is a more advanced form of living quarters than a space station in the sense that it is intended to be a permanent settlement or habitat. They are of two types, orbital and planetary. An orbital settlement is a colony in orbit around a celestial body. A planetary settlement is a colony on a planet or moon or asteroid.
Okay, so let us speak about the project month analysis. On week 0, we were introduced to our team. On week 1, we learned about the basic terms of a space settlement. We held elections for our logo and our team name. On week 2, we're deciding whether between orbital or planetary settlement, and we had an overview of our design. On week 3, we finalized our design and worked on the infrastructure and life support systems. On week 4, we worked on the final systems and reporting.
Now let's talk about location, design, infrastructure, and life support system.
Now let's talk about location.
Valerie Space Settlement consists of two parts, orbital settlement as well as planetary settlement. The orbital settlement is located on the L5 of Mars and the planetary settlement is located on the Mars as well as on Earth's moon. Now, let me give you a brief on what is Lagrangian points. The Lagrangian points are the points stabilized by the gravity of two celestial bodies. Now the question arises, why did we choose these locations? As mentioned earlier, the L5 point is the stable point and Mars is near the asteroid belt. We can also make a research center on Mars as well as on Moon.
Now, given the location, how do we get there? This will be done in 3 phases. First, a lunar base will be established on the surface of the moon, where the orbital settlement's construction will be completed. After that, the settlement will be propelled to L5 of Mars, and from there, small research establishments will be made on the surface of Mars. So in a nutshell, in the first stage, a lunar base will be established to extract materials for the construction. In the second stage, the construction of the orbital settlement will be completed in the moon's orbit. In the third stage, the settlement will be propelled to Mars's L5 and the initial phases of testing will begin. In the fourth stage, small colonies on Mars for research purposes will be established. After that, secondary and tertiary batches of people will arrive. And finally, once the settlement is fully functional, our focus will be on becoming self-sustainable.
Now let's talk about the design.
This is the design for an orbital settlement. There are like 5 main toruses. The first dark green torus is meant for wildlife torus. The light green torus for agricultural. The light blue for the residential place. The multiple torus for the for fun activities. And the small dark colored torus is for hotels. The huge orange color structure for the docking station. And the dark blue torus for the research center, and the pink color torus for the residential place for researchers and scientists who work in the research center.
Okay, so this is our approximate calculation for the surface area and volume of one torus, 284.24 kilometers square being the surface area and 4.80 kilometer cube being the volume of one torus.
For our propulsion system, we have decided to go ahead with the fusion propulsion system, and there are also going to be a number of fusion reactors on board.
Now let's talk about the Martian base. So our Martian base will be either underground and on the surface of Mars covered with a layer of regolith. This is to ensure protection from the sun's radiation as well as the enormous dust on Mars. And this is a basic idea of NASA's idea for lunar base for the Artemis program.
You can probably see us on the moon through your telescope. You're waving us at, we'll wave right back to you. Now let's talk about the phases of our settlement. The initial phase includes the research and testing of our settlement. The secondary and the tertiary phase includes the expanding of the settlement and becoming more sustainable. And the future scope includes the permanent settlement and the future operations.
12,000. This is the maximum estimated population in our settlement. Seems to be a pretty small number, but don't worry, you will have plenty of friends over there. This is the population percentage graph created by taking life expectancy, fertility, and some other factors into consideration. 20% of the population will consist of transgender people, 45% of the population will be of males, and 35% of the population will consist of females.
Now let's talk about infrastructure.
This is the internal view of the residential torus. We are going to go for Earth-like and homely feeling so that the residents can feel very comfortable.
So now, gravity is one of the most important factors here on Earth, and on the settlement, we'll be generating artificial gravity using centrifugal force. And this is the calculation for artificial gravity on a residential torus. The residential torus being of radius 3 kilometers will have to spin at a velocity of 0.54 rpm to generate the centripetal acceleration of 9.8 meter per second square like on Earth. Now, as I mentioned before, gravity is very important. You don't want to keep floating in the air all the time, do you?
For internal communication, that is communication within the settlement, we have decided to go ahead with the optical fiber net connection. And in the residential torus, there is going to be a metropolitan area network built. For external communication, that is communication with the Earth and the other research bases, the optical space communication method will be used, which uses laser rays as a mode of transmission of signals. And yes, we are aware of the problem of refraction of light in the atmosphere. So as a solution to that problem, we are going to be having one or more satellites in the Earth's orbit, which are going to convert light rays sent from the settlement to radio waves and sent back to the Earth.
So now let's talk about one of the other most important factors for life to exist, sunlight. There will be in our settlement, the sides of the tori will be covered with solar glass, and there will be 2 layers of solar glass between which there will be ozone gas to filter out the UV radiation. Behind the solar glass, there will be shutters and blinders to stimulate the day and night cycle.
For transportation inside the torus, we will be using bicycles for traveling short distances, and they will be producing kinetic energy which will be later converted to electrical energy. We will also be having buses and trains with glass ceilings so that the people can enjoy the beautiful view outside. We will also be having a vehicle which can purpose as a terrestrial vehicle as well as an escape pod.
We also introduced our own currency. The Valerie currency is also known as Astrobit. 1 Astrobit is equal to $1, and this is our logo. For the finance interface, we are building an app for PCs and phone which will track your transaction and maintain your accounts and stocks. We are also introducing a multi-purpose digital watch which can scan your transactions and can also check your vitals.
So now let's talk about life support systems.
These are the various subsystems required for life to survive and thrive within the settlement. The atmosphere will be taken care of by two systems, one for generating oxygen and one for cleansing the air. For agriculture, two techniques will be employed, aquaponics and aeroponics, which is mainly for fish and plants. Apart from this, livestock and poultry will also be there. Our main sources of electricity will be solar panels, solar glass, piezoelectricity, nuclear reactors, and kinetic energy from gyms. For waste management, we are planning to cut down on non-recyclable items, compost whatever organic waste is compostable, and incinerate chemical and industrial waste. For water, we are planning to extract water from the polar ice caps of Mars, icy asteroids, and also create it under lab conditions. Weather and climate as a whole will be taken up as a research subject, and as of now, we have come up with turbines for simulating wind, temperature and humidity sensors, and pressurizing units and airlock systems. Now, how do we obtain all the resources required? These are some of the methods that we would be using. Asteroid mining, mining the moons of Earth and Mars for minerals and other elements, electrolysis of water and carbon dioxide, mining of the Martian surface, and polar ice caps of Mars.
Now, one question you may be thinking about our location is, you're so close to an asteroid belt. What if an asteroid hits you? Don't worry, we've got your back. We are still researching on methods on how to prevent an asteroid which may be on a collision course with us. So don't worry, you've still got your back. And now let's talk about the medical care on board. We'll be having medical specialists from all fields of medicine, and we'll be having a med center or a med bay at initial stages of our settlement until it can be built and developed into a fully developed hospital. We will be researching on new methods like nanomedicine and robot surgery. We will also have emergency care facilities like ambulances. Now let's talk about future scope.
Wildlife tours. We are going to have a separate tours only for wildlife. This is to ensure biodiversity and to understand animal behavior in space.
We will be having recreational activities like gyms, parks, microgravity hub, and microgravity sports because they are very essential for our mental health. We will also be having a small tours containing hotels for visitors to live in.
Last but not the least is the main aim for future scope, that is becoming self-sustainable. The average building time of our orbital settlement is more than 20 years, and the estimated average cost of the whole settlement is estimated to be around $250 billion. And we would like to point out that this is a global project in which several companies and countries are going to be investing in, and we are interested in investors and sponsors.
So now, me and my team thank our supervisors, Manisha ma'am, our main supervisor, and Deepthi ma'am, our co-supervisor, and a special thanks to Geeta ma'am and Sujay sir for organizing this wonderful event, Tejas sir and Mahesh sir for helping us with our project, Agnishike ma'am for educating us about the wildlife tourists, and Dakshay sir for being with us during our meets. We really appreciate your guidance throughout this project. So now let's beam us up, Scotty. Let's boldly go where no man has ever gone before. We'll see you there. And thank you. That is all. We hope you enjoyed our presentation. We are now open to questions.
Thank you so much, team. That was a wonderful presentation. So, do we have any of the guests here addressing the team first before we go ahead with the Q&A session?
Yeah, so it's a well thought out plan, and I really appreciate the students taking time and researching on it. And still a lot of things have been are still under research when it comes to Martian base as well as the lunar base. But I could really see that they have gotten into research on different aspects of human settlement in both the places, which is really appreciable given their age and the kind of experience they might have. And I think it's a very good initiative by SSERD as well. So I really appreciate the team. Thank you.
Thank you so much, sir.
Thank you so much, Ramesh. Nice to have that very good feedback. It kind of motivates us to run more. So do we have any of the guests making any suggestions for the team to work ahead with the project as to how to proceed?
Yeah, Sudhir here. Kids, all the best for you. Good imagination. Maybe some of the things may get realized soon, and some of the things probably we will shift it to your generation. By the time you people come out, probably I think you can implement. Definitely, some of the things may not be possible in our tenure. Good imagination. Supplement them with the possible threats in the space, whether it is moon colonization or Mars colonization or asteroid colonization or space tourism. Some of the things, you can confine yourself for the space tourism. Okay, you categorize them because all the surfaces, all the terrains would not be similar. The temperature conditions, the gravity conditions, the pressure conditions would be different. Consolidate them for different concepts and put it forth as a document. This could be an imagination from the kids, what kids will imagine how their life would be after 20 years or 30 years or 50 years. Okay, good. All the best.
Thank you, sir. We'll take your suggestion into consideration.
So thank you all so much. So without further ado, let's go ahead with the Q&A session. So we have the first question from Madhuri Tamam. Yes. Team, ma'am wants to know how will you generate oxygen on board?
I'd like to take up your question, ma'am. Oxygen will be generated by the electrolysis of water. So as we all know, water consists of 2 atoms of hydrogen and 1 atom of oxygen. So by allowing electricity to pass through water, the atom will recombine and separate into the hydrogen atom and oxygen atom. So the oxygen will be used for breathing, and the hydrogen combined with methane will be used to regenerate water used for producing oxygen. Hope that answers your question.
Yeah, that comes to the next question. Where will you get water from?
Ma'am, as we mentioned, water will be extracted from the polar ice caps of Mars. We have also devised some reactions, some chemical reactions that we'll be using to create water.
No, I mean water on board the space station, on board the Taurus, not on the planet.
Yes, ma'am. So, okay, to give you an example, we have come up with some chemical reactions which would be undertaken in the labs present on the orbital settlement.
Okay, ma'am wants to know that you are right now describing how you'll be generating oxygen for the terrestrial settlement. So how will you be doing that for the orbital settlement?
Yes.
Will you be transporting water, or would you be transferring the resources from your terrestrial settlement to the orbital settlement? That's what ma'am wants to know.
Okay, ma'am, actually the terrestrial settlement is not a settlement exactly. They are research bases. So our main residential settlement is the orbital settlement. So we will be, so the orbital settlement will be independent and the terrestrial settlement will be independent. And all the resources will be, extracted in a way that it could be used independently by each of the
okay, what I mean is that in the orbital settlement, both oxygen and water are precious resources.
Yes, ma'am.
Very precious. So making oxygen from water or water from oxygen makes no sense because you need both.
Ma'am, I would like to add a point. We are also considering electrolysis of carbon dioxide from the Martian atmosphere, since Martian atmosphere is composed of 96% carbon dioxide. So we're also considering electrolysis of carbon dioxide to generate oxygen.
Yeah, that is a good idea for Mars. Yes. But on the orbital station, you need to prevent CO2. You see, what I mean is a how to sustain habitable conditions on the orbital station so that they will be, in harmony. Both water and oxygen, something has to generate oxygen continuously, isn't it?
So, ma'am, we are also having plants and shrubs and everything on the settlement in our residential torus. So, apart from, we are still working on methods of electrolysis and other methods of producing oxygen.
And to add upon that, we are still doing the research on some topics. So if you have any suggestions, ma'am, please give us so we can work on it.
Okay. Yes. Thank
you. Plants are a good source of oxygen.
So that's one way of putting it. Okay. Thank you so much, team. Again, we have another question by ma'am. This is very interesting. So given a choice, where would you prefer to live? Is it terrestrial settlement that you choose or an orbital settlement, and why?
I think Tanvi can answer this.
Yeah, I would like to answer this question. So this orbital base is actually, you can say it's kind of like a research settlement. So this will serve as research for future settlements. Obviously, we don't know much about exoplanets and we cannot directly go and land there. So we will need to conduct research and consider options like terraforming Mars and everything like that. Also, having a settlement on a planet also has its own disadvantages. As you said, ma'am, artificial megastructures also have their own restrictions. Planetary too have their own restrictions, and according to us, it's a bit more risky since stimulating Earth-like conditions on a planet is a very huge task. So we wanted to firstly do artificial orbital settlement and then move on to planetary.
Madhurita ma'am, do you want to add any points to
that? Actually, I've written one article about artificial megastructures versus habitable planets. I will pass this. It's a small article in the astrobiology newsletter, and the basic idea is that in principle, all the artificial megastructures, especially Dyson sphere, they're very unstable. They're very unstable dynamically, and there are many other problems. So it's much easier actually to give a push to let's say Mars, to push it a little bit because it is outside the habitable zone, but not too much out. So it is all this energy. It is better to push it a little bit into the habitable zone of our sun and start living on Mars. That is the basic idea. So that's why I asked this question.
Thank you so much, ma'am. Okay, next we have a question on what do you mean by simulating day and night on your settlement?
Kirtina can take this question.
So by what we mean by simulating day and night is that we want to, how we have the day and night cycle on Earth, we want to create a similar type of day and night cycle on the settlement as well. So that is what we mean by that, which would be done by, as we had mentioned in our presentation, we have solar glasses for allowing sunlight to pass through, which would simulate daytime conditions. And then we have shutters, which would be closing the solar glass so that it can create nighttime conditions.
And to add upon that, it is very important to have a healthy lifestyle out there.
Thank you, Team Valerie, for that wonderful presentation. Now we have with us Team Entrepreneurship, who have been working on developing a bike, basically a motorbike for different terrain conditions. So without further ado, I invite the last presentation for the day, but not but not it's no less to any of the presentations that we have had today. So without further ado, I invite Team Marceline to go ahead with their presentation. Do we have Tanmay?
Yes, sir. I hope my screen is visible.
Yes, Tanmay.
If we can see the horizon, we want to know what's beyond. A quote by Buzz Aldrin. Good afternoon, ladies and gentlemen. We are Team Marceline from the Entrepreneurship Group, and we would like to showcase before you our research completed during the JSS program. We request all of you to accompany us throughout this presentation, and please use the link to post any questions that you might have. But first, a bit about us. We are a group of young entrepreneurs coming from extremely diverse backgrounds, yet sharing a common goal. Our members are distributed over a variety of age groups ranging from middle school to colleges. In fact, one of the most valued members of our team, Tanmay Kumar, studies in grade 7 and is one of the youngest members of the JSS program. Team Marceline is supervised by Nikita ma'am and co-supervised by SE sir. Jitavadi Das is our team leader, Siddhanta Huja and myself, Aeronautics. We are the assistant team leaders. Our team consists of the following members: Tanmay Kumar, Sujal Gaur, Shrujan Gade, Gargi Pawar, Dishake, and Pranav Vinod.
This is the flow of events for our presentation. We will start off by introducing the aim and objective of Marceline, then move on the discussion about the three main pillars of our research: the market analysis, our business strategy, and the design of the products. And would like to end the presentation by displaying our target timeline and our future goals. And finally, by answering your questions. So without further ado, let's get started. Here are a few terms we would like to introduce before we dive into our research. Entrepreneurship is defined as the act of starting and running your own business, or a tendency to be creative and wish to work for yourself in your own ventures. Whereas the activity of traversing the surface of a heavenly body using specially designed vehicles is known as extraterrestrial travel. Marceline is formed by the conjunction of two words, Mars and Selene, denoting the moon and the red planet. Our team's name thus reflects our desire of dominating extraterrestrial travel on both the moon and Mars. Our problem statement to start up a company focusing on building ATVs for the Martian and lunar surfaces. We focus on quality production while keeping down the cost of manufacturing. Our objective is to develop ATVs capable of traversing the lunar and Martian terrains, as well as to develop a range of modern space-age bicycles to be used on Earth.
Your screen is not set anymore. Can you please share your presentation? Take a minute. It's okay. Pause a minute.
So this is our market analysis for our products. We first differentiate between upstream and downstream industries. So basically, upstream industries provide carrier and launch facilities to other space companies or design launch vehicles. The downstream industries provide services such as satellite communication and also work in operation sector. According to our research, the major sectors in the upstream industry are manufacturing, ground station, and workstations. And the downstream in the sector, as previously mentioned, mostly constituted by the service and operation sectors.
We would now like to discuss the main raw material of our product, which is nitinol. Nitinol stands for nickel titanium. Nitinol was invented by William Bueller in Naval Ordnance Lab in 1959. It is a shape memory alloy, that is, it displays thermally induced martensitic transformation. It occurs when the crystal changes its orientation from austenite to martensite state. This results in nitinol being a shape memory alloy. The superelasticity stems from another property known as stress-induced martensitic transformation, or SIM. Thus, even though nitinol seems to go through plastic deformation, it can snap back into its original shape when the temperature is increased or the stress is relieved.
So, moving ahead, due to these properties, we plan on having the example set by NASA and using nitinol as the material for making wheels for all our products. There are a couple of advantages of using this. Nitinol wheels will not get permanently damaged on the rough terrains of the Moon and Mars. They will be airless, so a change in pressure will not affect their functioning. They will be
Hey,
lighter, so the wheels
one
can
second,
move
sorry to
at
ask.
even so the
Is
wheels
the
can move at,
Sujal,
can
you're
I
on mute.
continue?
You were on mute. Yeah, please continue.
Yeah, sorry. So they will be lighter, so the wheels can move at even faster speeds. And finally, nitinol wires are relatively cheap, so the cost of the production will not be raised substantially. The source of energy used by our lunar and Martian ATVs are solar power, piezoelectricity, electromagnetic induction, and we also plan on developing thermoelectric and nuclear power. The wheels are following a rubber-less policy and do not depend on conventional sources of energy like fossil fuels. Hence, our products will not harm the environment, neither on Earth nor elsewhere. So, we plan on having solar energy as the main source of energy for our ATVs. But as Mars is relatively farther away, we plan on using some auxiliary power sources as well. We'll be including piezoelectric transducers and an apparatus for electromagnetic induction as well. All of this energy will be refined using a solid state full wave bridge rectifier circuit and can then be stored in a lithium ion battery. We also plan on using energy produced from nuclear decay and thermoelectric generators. Here are a few designs that our team members have made. On the left is the design of the bicycle, and on the right is the approximate design of the wheel for the ATV. This is our market research. We found out that major space agencies like NASA and companies like Smart Tire Company, along with Mercedes-Benz, a company traditionally known for making luxury cars, will compete with us and the potential to form a strong foothold in this market. What differentiates our company from our competitors is our dream to make vehicles available to the common man, while projects undertaken by NASA can easily go north to $2 billion.
In order to understand the different aspects of developing a successful startup, the team members decided to draft a business strategy. The business strategy is a convenient method of listing the various aspects of the business and conveying these aspects to an investor. The business strategy for Marceline covers the following aspects. The key partners. Marceline wishes to partner with companies that produce the raw material for the vehicles. That is, nitinol manufacturing plants, automobile manufacturing plants, etc. Key activities: manufacturing the vehicles, the ATVs and the bicycles, and constantly researching about new technology and developing new designs. Key resources: nitinol, automobiles, either completely built or individual parts of the same, along with the location for the warehouse, are the key resources required for building the product. Value propositions. The team members will build a product that is affordable, lightweight, unique, and environment friendly. Customer relationships. Customer relationships are very important for a company and determine its value and place in the market. Recognizing this fact, Marceline will ensure customer satisfaction by providing prompt service as well as having a YouTube channel dedicated to discussing quick fixes for the products. The company will hold regular webinars and answer questions about their products as well. Channels. The products will initially be made and dispatched from the warehouses of the key partners, but at a later stage, these processes will be moved to Marceline's own headquarters. The products will be initially advertised via social media websites, the company's own website, and blogs. The customer segments. Since the products being low cost is a key value proposition, Marceline will be targeting the middle class people and the youth for the sales of the bicycle, whereas the ATVs will be sold to space agencies and the future space settlements. Revenue streams. The main revenue streams for Marceline are crowdfunding initially and angel investments ultimately. The social media revenue can also be added to this sum. The crowdfunding websites that the team has shortlisted for running a campaign are Crowdfunder, Kickstarter, Fuel a Dream, and Indiegogo. And finally, the cost structure. The team calculated the gross cost price, the sum of the cost prices of all the raw materials, and after including the overhead charges and the grants given by the government as a part of the Startup India campaign, the total cost price is approximated to be very close to rupees 50,000, and that is for the bicycle. The selling price of the bicycle can vary depending on the number of features it has or the model.
We have developed a comprehensive target timeline for our products for the next 5 years. We have divided each year into 4 quarters, representing our progress on the product. We will be manufacturing 3 different products over a targeted period of time. That is a traditional bicycle with the application of Martian and lunar technologies on Earth, ATV for the lunar surface, and ATV for the Martian surface. The business expansion plan extends to over 5 to 10 years, taking into account the launch dates of various space-related programs. For example, the launch of the Artemis 3 mission on 2024, SpaceX Mars launch on 2026, NASA Mars launch on 2033. As these programs can be turned into opportunities to be used to accelerate sales. The timeline features a perpetual cycle of research and development, building the prototype, meeting with investors and sponsors, manufacturing, marketing, and launch of the products. This process will be followed in order to ensure that the product is of high quality and affordable at the same time.
As a team, Marceline aims to find alternate source of energy, as discussed in the group meeting with Bellatrix Aerospace co-founder, Mr. Rohan. We have also conducted a market survey, and though it's still in progress, the results have bolstered our beliefs in our product. Here are a few results from the survey. Under the concessions provided by the government under the Startup India campaign, we as a team plan to register under this program and compete to gain grants for our startup.
Everyone, this is all what Team Marceline has achieved in the 4 weeks of the GSS program. We are thankful to the Society for Space Education, Research and Development for organizing the Junior Space Scientist program and presenting us with this wonderful opportunity to showcase our talents. We are grateful for our supervisor, Ms. Nikita C. Ma'am, and our co-supervisor, Mr. Yasir Sir, for inspiring us, constantly motivating us to think big and reach for the skies. We express our heartfelt gratitude to all the mentors and guest speakers for organizing the training session for the GSS program. These sessions were very informative and equipped us with skill sets required to complete our research. Last but not the least, we thank each other, all the members of Team Marceline, for cooperating with each other and making this project a success. Without the constant support from the entire team, the completion of this project would not have been possible. Thank you, everyone. Thereby coming end to our presentation. Now we're open for questions.
Thank you so much, team. That was a wonderful presentation. So before, again, we proceed with the Q&A session, I would like the guests to address the work done by the team. So basically, Entrepreneurship team, they're planning to come up with a startup that can focus on futuristic bikes. So if we are to go for future terrestrial settlements or further exploration, they want to start off with a bike here on Earth, then move on to different terrain. So that's their concept. So do we have Shashidhar sir and Sudhir sir addressing the team?
Okay, team, entrepreneurs, team, I'm happy at least you thought of something which is worthwhile outcomes of the thing. The one suggestion I wanted to give to all of your kids is, please think of indigenous, our missions, okay, ISRO missions, because we are all Indians. First think of India and then go for NASA, ESA, whatever these things is, because that is some kind of what you call our own land, okay. That is one aspect. For you to understand, there are several technologies available from the different space agencies at free of cost or maybe affordable cost. you look at those technologies, because these technologies give you some kind of spin-offs which can be put it to use for the social causes or normal community requirements. And you can develop on, because whatever you said, some material, this carbon composites, many of the materials are there, even special alloys, which will definitely increase the strength to weight ratio and can be made use of. In fact, Jaipur food, we have used the same thing. Even there are chances that LVDs for biomedical equipment, the some of the spin-off applications can be. Please go through, just note down technology transfer, just Google it, because first stop Googling it, go to basic research. Okay, Google will give you, it is a search engine, it should take you to the sites, and if you pick up the ideas from Wikipedia, such kind of things, it will stop your thinking process. Okay, because I could make out, because kids are very used to Google engine, immediately they will go and they will jump into the conclusions as if that is only the actual thing. But go to the respective sites and see whether you wanted to use this as a material, because there are n number of applications which are used for your societal applications. Maybe if you go through such kind of things, you yourself will think, okay, this particular thing can be made use of for social applications. Okay, that is my suggestion. Okay, good job done. At least you get to know what is the business model, how to raise the fund, what is the commercial viability. At least it's very, unless otherwise you go through an MBA process to understand all those things. I think your mentors have done a good job. That's what I can say. Okay, to lead you through a critical platforms or critical milestones. I think they have done job very well. Please take the same supervision from the same mentors and try to understand what is the materials that are available for technology transfer. Those kind of things, you can make it applicable for your day-to-day life. Okay, all the best team. Thank you.
Thank you. Actually, we did have a training session on telling these people as to what kind of material are they to find and how to find, where to find, and what is the right information.
Basically, see, my suggestion is, don't think immediately space means moon and Mars. Don't think like that. Space, even though we develop a lot of items for the space, 90% of the items will have social value. Please look at that. And space applications, see, when you are talking about the business perspective, if you take the space domain, Nikita can share you with Bryce reports. See, when you take the space domain, if 360 billion is the total revenue or space business, out of which 9% is only the launch vehicle and 12% is only the satellite manufacturing. See, everybody has got a fancy just to jump into satellite production, launch vehicle production. It's not required. Space applications, because you people are talking about coding, people are talking about the software tools. It is nice that people are talking about Python, 3D Max, such kind of softwares. Please use the space application. Try to identify your pet dog, where it is gone. Try to identify where your friend is. Okay, when he is traveling somewhere, try to identify your material, whatever study material that can be put it on a group using cloud platform and share it without printed material. See, such kind of things everywhere. The space have got an application with a small gadgets. Okay, think in that line, because marketability will be more. Many of you can become young entrepreneurs with cottage industries. That's how China has developed. How China, each and every house is a cottage industry. By the time another 4 to 5 years rolled out, if you start thinking in the same spirit, definitely each and one of you will become entrepreneur, and it will become a cottage industry. India will grow like anything economically and industrially. Okay, don't think that the space means only satellite and launch vehicle. There are 80% of the thing which you can do with small electronic systems, software and applications. Okay, I hope Nikita and Sujay will guide you rightly. Many more such kind of workshops are required for you to get into the platform. Okay, all the best. Thank you. Thanks a lot. Very nice presentations. Thank you.
Thank you very much, sir. Thank you very much.
Thank you, sir.
Yeah, Tejas, I have one suggestion for Nikita and Sujay. So, all these people are thinking in the right direction, and they have been guided really well by SSERD team. I would suggest you to please collate these ideas and then separate it into research topics and publish papers. Start publishing papers, so that there are a lot of conferences that happens for both school students as well as college students. Don't waste this presentation and let it fall away right after this. Capture it and publish as papers in journals and all. So just to encourage them also as a habit. And India lags behind in publishing papers. They don't do much, especially for Mars exploration or any other space exploration missions. Not much. So we should do that actually. So yeah.
We will, Ramesh. Again, thank you so much for that suggestion. And the whole objective of this whole program, working online, is that they come up with some kind of paper that could be published, and also participate in the competitions that are happening around. And the team have been, few teams at least, have already selected where they have to go and compete or where they have to present. At the same time, the students are also trained on writing, how to write the research papers. In fact, how to find these research papers and study only that and not Wikipedia. So this kind of effort has been put up by the whole team, and I'm pretty sure the students will take it forward.
Awesome.
Thank you.
All the best.
Thank you.
Thank you so much, Ramesh and Nikita. And yes, Shashidhar, sir. Yeah. Okay.
Yeah, thank you. It was very informative and very invigorative for me, and to see the youngsters of our country, a chosen few, excel in these skills. I have a few things to tell. I want to build up on Sudhir Kumar's comments as well. Very well placed. In our mythology, there was something called Pushpaka Vimana. They were flying. We had aircrafts in the past, which is actually true. Maybe there is no model of that existing, but our Talegari literature has every description of this. I heard NASA picked up this diagram from our Talegari and designed a spacecraft which doesn't have wings, and then put it in their turbine, gas, GTRE, something, wind turbine, and it levitated. So there are several proofs. So you can think differently. Every spacecraft need not have a wing conventionally. So dig deep into our mythology. You may find something in Sanskrit literature. Second thing is, don't do Google too much. It kills your creativity. And you just go Google as much as needed and use your brains. Your brain is better than Google, and collectively you are more intelligent than individually. Actually, Rotary has a structure to enable creativity. We have Rotracts and Interacts. So if you can join Rotract Interact, Nikita's team and our team can enable you to succeed. And once we succeed, the whole country goes forward in many ways. One thing I have immediate use is the alloy that Sudhir Krishna mentioned. We have an artificial limb center in Ramaya College, where we want to print 3D legs for needy, for poor people or anybody who loses a limb or a hand. We have already got a global grant for that. We want to use the alloys to make it happen, rust proof and color matching the skin of the other leg or the other limb. Then many of these space technologies actually will be useful for our farmers. The vehicle that you're designing for the moon or the terrestrial planets, extraterrestrial planets, can be used by farmers. It's a lightweight harvester, paddy harvester, for example. This is for the entrepreneurial team. Why don't you start making money out of the vehicles designed futuristically for the space, but immediately used for the farmers? Farmers in dire straits for lack of labor. Labor is very difficult to find in villages. Space drone or something to capture the moisture status or disease status of plants in a coconut garden or a areca garden. So think globally, but act locally. There is a lot of opportunity for the kind of thinking that you're doing. Collective intelligence, I find it very good resource here. Thank you very much. God bless you all, and please go ahead.
Thank you, sir. Thank you so much for that wonderful addresses. So we'll proceed with the Q&A session. We have a few questions posted up here on the screen for Team Ask Team. So the first question we have from an anonymous person. So why ethanol and why not other products? Team?
I take that question. Nitinol has some properties that we feel will be useful for wheels on the Martian surface. First, it's a super elastic material. So as it was mentioned in the presentation, it shows stress-induced martensitic effect. So that is, whenever the stress is relieved, it changes its state from austenite to martensite and back. So even though it does seem like it's going through a plastic deformation, it retains its original state. And since the Martian terrain is an alien terrain for us, that's why we thought that nitinol would be a good choice there. And we are aware of the fact that there are other super elastic and shape memory alloys as well, but nitinol is comparatively cheaper. Another example is a gold cadmium alloy, but that is very expensive. So that's why we decided to go with nitinol.
Thank you.
Nikita, I have a point to make. Can I use 30 seconds?
Sure, sir.
Yeah, so I think the world is, I don't know whether you have looked at the drone technologies have taken over everywhere, whether it's defense, agriculture related, utilizations, or e-commerce is becoming big time. People are sitting at home and buying everything, and US Amazon has started delivering using drones. Okay, and even cabs, where if from Electronic City to airport, if we have to travel, looking at the traffic and all that, we have drone cabs as well might come up in the next 5-10 years. I think that is something which might be interest, and also if we are looking for angel investors, if you start looking at drone technologies and drone delivery sort of thing, it will help a lot of agriculture related farmers, defense, as well, and then lot of applications. I think that is one interesting project I think you guys have to start looking at than this solar aircraft is what my feeling is, but you can explore further.
No, thank you very much, sir, for that point. For this particular cohort, we chose these topics, and we have next cohort literally starting off in another 1 week, and that's for students from another country. We keep exploring different topics, and this is one of the topic which we already have in our list. And Sujay has been personally doing research on this, like initial research on how we can give this to students in what form, and we will be taking off. And thank you so much for the suggestion, and thank you for your time for being from the beginning. Yeah.
Thank you so much, sir. Okay, we have another question in the chat section. I guess it goes with the same question which Shashidhar sir asked.
I think Siddhant can answer this, or Shrujal can answer this, if they would like to take this up.
This one. Yeah.
So, related to the toppling of the four-wheeler vehicle, yes, we have recognized that fact because the Martian terrain is quite
Go ahead, Siddhant.
Thank you. Yes, so we have recognized the fact that if this four-wheeler vehicle topples, then so we do plan on including a gyroscopic mechanism, which but since our project is in a very initial stage right now, so we just developed the chassis and the wheel design. And yes, sir, we will be using the gyroscopic mechanism as well.
Okay, there's another question in which Venkat wants to know the cost of your rover.
The cost structure for the bicycle, because that's the first stage of our vehicle, has been developed right now. And the cost price is close to 50,000 rupees. But the research and development for the Martian and lunar ATVs, as was displayed in the timeline, is spread over the next 5 to 10 years. So yes, we'll be researching and developing, and we'll be finding new technology to lower down the costs.
So I guess that would be it. The other questions look like repetitions of the previous ones. So thank you so much, team, for that wonderful presentation. So we come to the end of the program. So before we end our today's session, we have a look back video wherein we'll have a look at how the entire program worked, wherein all these students, how they all met. They were exposed to training programs, not just working on problem statements. They were asked to meet guest speakers, wherein guest speakers came in and gave their inputs on the project that they had worked on. And also they have been working day in and day out to come up with this wonderful presentation in such a short span of time. That is, even for students at undergraduate level, it kind of seems very difficult. So given their age, they have, I dare say that they have done a wonderful job. So Dakshish, can we have the look back video, please?
Listen up. Give me a go, no go for launch. Booster. Go. Retro. Go. Vital.
We're go flight.
Guidance.
Guidance go.
Surgeon.
Go flight.
Ecom.
We're go flight.
GNC.
We're go.
Telmu.
Go.
Control.
Go flight.
Procedures.
Go.
Inco.
Go.
FAO.
We are go.
Network.
Go.
Recovery.
Go.
Capcom.
We're go flight.
Launch control, this is Houston. We are go for launch.
A famous man once said,
I am very aware of the preciousness of time. Seize the moment.
let's track this from the beginning.
Things are right, and you just know there is something in your eyes that brings me home. 'Cause when there's love, you don't let go. So as long as you're with me, you're not alone, you'll never be. I wanna tell you what I feel and really mean it. I wanna shout it from the rooftops to the sky. 'Cause if you ever need a friend, you know I'll be it. From tonight until we see the end of time, I'll cross my heart and hope to die with. Always and forever, I'll be by your side. When days are you ever need a friend, you know I'll be there. From tonight until we see the end of time, I'll cross my heart and hope to die with. Always and forever, I'll be by your side. When days are dark and stars don't line with. Always and forever till the end of time. I'll cross my heart and hope to die with. Always and forever, I'll be by your side. When days are dark and stars don't line with. Always and forever till the end of time.
It was completely dark, with the moon which was in spark. It was where the galaxy was visible, and my true side was identical. It was a complete silence, with no traces of violence. It felt so lonely. At the same time, it felt like eternity. It was my time, and I was only mine. With no relation in my mind, I was only with me and my kind. The unknown that controls your sleep, the fire that disturbs your sleep, the empire which you want to build, for that you should have dreamed. Under insomnia and tiredness lies 1,000 sleepless nights. On the way to the future, I cry for the days so that my brain lies. I want to sleep, but my eyes doesn't tire. I want to sleep, but my brain is on fire. I want to sleep, but my thought denies. I want to sleep, but my sleep dies. In the search of success which I visualize, I forget the present which every day rise. My brain loves to think, such that it opens the way to overthink. I want to sleep, but my dream denies. I want to sleep, but my sleep is ice. I want to sleep, but my bed asks me to stay up. I want to sleep, but my clock says, it's 6 o'clock, hurry up. It's what the nighttime feels like, where the thoughts can totally hike in the mountain of the brain, where everything is dark, and only you can give yourself one thing, that is a remark.
Every time you come around, you know I can't say no. Every time the sun goes down, I let you take control. I can feel the paradise before my world implodes. And tonight had something wonderful. My bad habits lead to late nights sitting alone. Conversations with a stranger I barely know. Swearing this will be the last, but it probably won't. I got nothing left to lose or use or do. My bad habits lead to white eyes stare into space. And I know I lose control of the things that I say. Yeah, I was looking for a way out, now I can't escape. Nothing happens after 2. It's true, it's true. My bad habits lead to you. My bad habits lead to you. My bad habits lead to you. Every pure intention ends when the good times start. Falling over everything
One of the great revelations of the space age has been the perspective it has given humanity on ourselves. When we see the Earth from space, we see ourselves as a whole. We see the unity and not the divisions. It is such a simple image, with a compelling message: one planet, one human race. We are here together, and we need to live together, with tolerance and respect. We must become global citizens. I have been enormously privileged, through my work, to be able to contribute to our understanding of the universe. But it would be an empty universe indeed, if it were not for the people I love, and who love me. We are all time travelers, journeying together into the future. But let us work together to make that future a place we want to visit. Be brave, be determined, overcome the odds. It can be done.
That was pretty nostalgic. Okay, I'll give it to that. Yes, the video.
By the way, I just want to share that thank you for featuring the poem. It was really amazing and really good surprise.
Pleasure is ours. Thank you so much, Dakshish, for that amazing video. It's Dakshish who has worked on it, so he deserves all the credits for it. And I would like to thank all our guests who have been, with us since the start of this program. It started at 10, and we are almost hitting 1 right now. And it has been 3 hours straight without any breaks. So that takes a lot of commitment, and I really appreciate all the guests right over here. Out of even despite their busy schedule, they have made time to come and watch the presentations made by our students. Thank you so much, everyone. Shashida sir, Sudhir sir, Margarita ma'am, Ramesh sir, everyone. I mean, all of you who have been here for this session for so long. So with that note, I would like to end the session. So it gives me great grief that good things, or like all good things, come to an end. Even this should come to an end, but it quite not literally be. You all are still free to go ahead with your projects, regarding which the details of which we will be discussing in the evening session. So make sure you join at that time. So for now, we bid adieu. Thank you all for joining in. So it has been an amazing session. Thank you all. Have a good day. Bye-bye.
Thanks to everyone from our end again. And we're good to go. See you all in the evening.